Hi, I'm Woody, and together in this course, we'll be covering all the most important concepts and techniques that you'll need to use statistics effectively in business, data science, and, I believe, life. I've worked as a mathematician and statistician for over 10 years in a range of sectors, from economics to politics to sports analytics. I've taught these subjects to thousands of students in person and tens of thousands online. The amount of data available to us is increasing year on year exponentially, but this is only as useful to us as our ability to understand and interpret it. We're not born with good instincts when it comes to statistics and data, which is why understanding how, when, and why to use mathematics is essential if we are to extract the signal from the noise in our data. In this course, we'll be covering the three most important concepts that you need to use statistics effectively: data analysis, data visualization, and probability. Along the way, I'll also regularly be showing you how to use Microsoft Excel to put everything that you've learned into practice. This course is aimed at people who want to use statistics to make better decisions. Whether you work in tech, finance, run your own business, are studying, or just find this stuff fascinating, this course will give you tools and techniques that you can put into practice straight away. It assumes no prior knowledge of the content and is suitable to those of you new to statistics. But it's also great for those of you who want to extend or sharpen the knowledge you already have. I really hope you enjoy this course and find it useful. Feel free to read the course description, and I look forward to seeing you inside. Hello and welcome to this part of the course in which we will look at descriptive statistics. This is the branch of mathematics which gives us some tools and techniques for analysing data and describing it, as the name suggests. One example of a descriptive statistic you're probably already familiar with is an average. So an average describes the data that you are working with. In this chapter of the course, I'm going to focus mostly on what these different statistics mean. We're going to do a little bit of work calculating, often in Excel, sometimes with pen and paper, but the focus is on helping you understand what the different descriptive statistics mean, what their limitations are, how to understand them, and where and when to use them. So in this chapter, we will look at the following things. We'll look at the mean average, something that you hopefully remember how to do. We're going to focus, of course, on its limitations. Obviously, we'll look at how to calculate it. We'll look at its limitations, when and where to use it, what could go wrong when using it. Next, we're going to look at the median, a different type of average, again, with a strong focus on what it means when we've calculated a median, when we should, where we shouldn't use it, that sort of thing. Then we look at the mode, a third type of average. After that, we're going to look at quantiles, range, and interquartile range. So these are some ways in which we can measure the spread of data. After that, we look at a slightly more complex form of measuring the spread of data, standard deviation and variance. Once again, trying to steer clear of any scary, nasty formulas where possible and focusing on intuitions and understanding. Next, we look at something called the coefficient of variation. It's a slightly more nuanced way of measuring the spread of data. Then, the most technically challenging part of this chapter, we look at two concepts, skew and kurtosis, that help us analyse and describe data at a more sophisticated level. Finally, we look at correlation, so just a way of measuring correlation, a descriptive statistic that applies for bivariate data. That's when you've got two things that you're measuring. So let's jump in and take a look at the mean. So the mean average is probably a concept you're already familiar with. When you have a bunch of numbers like these and you want to work out the mean average, you simply add them all together and divide by the number of terms you have. In this case, there are 7 terms. When we divide by 7, we get 39. So it's pretty easy to do with pen and paper, but obviously there is an Excel function for this as well. So in Excel, if you want to calculate the mean average, you just use the average function. So the one they call average is the mean average. You just select the data you want, and that is your mean average of 39. Now let's talk about the notation we use for this. So The formula for the mean average is this. We often use the Greek letter mu to represent the mean average. And what's going on here? Well, the mean average is sigma x. So sigma means we're going to add up. So it's the sum of all of your data points, and x represents each of your individual data points. So this just means add up all of your data points. So that's what's happening up here. And then we divide by n. N is the number of terms you have. In our case, it was 7. So now is a good time to also introduce the distinction between population data and sample data. Now, this can be a little bit confusing. I'll try to keep on coming back to this through this chapter so that you get a good sense of what this distinction is. Very often when we're working with data and statistics, what we actually have is a sample of data. So let's say that, for example, I was interested in ages of people working in a particular factory, for example, and I took 7 people and I worked out an average of 39. Well, those 7 people were not everyone in the factory. They were a sample of people who worked in the factory. So that would be a sample. What would a population be in this context? Well, the population in this case is just all people in that factory. Population doesn't always need to be of a country. It can just be the full data set of whatever it is you're interested in. In most cases, you don't have access to a full population. In the case of a factory, maybe you could sample everyone, but there are certainly cases, suppose this was in fact the weights of a certain type of animal. Well, if I've sampled 7 and got an average of 39, that's the average of my sample, the full population would just be every single individual in that species. So clearly, in many situations, populations are not possible. Now, we have slightly different terminology, or at least notation, for when we're working with populations and samples. So when you see X bar, which is actually the more common thing to see, that suggests that we're dealing with the average from a sample. We also often use little n rather than big N. Big N often refers to the size of the full population, which we often don't even know. Little n usually refers to the sample size, or to the size of your sample. So just a note to point out that difference. You'll see both of these. Mu tells you you've got the entire population. X bar means it's a sample. Okay, so let's look at data when it's grouped up in a frequency table. So this same set of data could be written in a frequency table like this. So we only had one data point at 30, we had 2 data points at 32, we had 1 at 37, we had 1 at 42, and we had 2 at 50. So if you want to work and calculate the mean average from a frequency table, well, rather than writing it out like this, what we can do is we can group our terms up. So rather than those 32 plus 32 and the 50 plus 50, we can rewrite that like this. We say I've got 2 lots of 32 and I've got 2 lots of 50. And of course, we get the same answer. And the reason for doing that is that there are some frequency tables where it would just take up a lot of space to write down all of the different data points added up. For example, this one, suppose I've got ages of some students in a school and the frequency for each one. I don't want to write 14 plus 14 plus 14 plus 14 76 times and so on. So what I can do is just use this formula. I've got 76 14-year-olds, so 76 times 14. I've got 121 15-year-olds, so 121 times 15. I've got 118 16-year-olds and so on. So on the top of the fraction there, that's just the sum of all of their ages, and I need to divide by the number of data points I have. And the number of data points is just the sum of the frequencies, because this tells me that there are 76 14-year-olds, there are 121 15-year-olds, and so on. So the total number of students is just all of these numbers added up. And we can use that slightly shorter version to calculate an average. I say shorter, it's just shorter than writing out 14 plus 14 plus 14 76 times. So we often will use this formula for this, which is just an alternative way of writing the mean. So when we write sigma fx, it just means it's the sum of the frequencies times by whatever the values are. So it's a frequency multiplied by an age, a frequency multiplied by an age. It's f times x in each case. And we're dividing by the sum of the frequencies because, as discussed, the sum of the frequencies is just the size of your sample. And we can do this in Excel as well. So in Excel, if we want to do what I just showed you before, we want to multiply each of these ages by the frequency. Now we don't need to do that separately. We can use Excel's function sum product. So what sum product does is ask me to select two arrays. If I select this array and this array, it's going to multiply each pair of numbers and then add them up. So that's the sum of all the ages in the school. And what I want to do is I want to divide this by the sum of the frequencies, because the sum of the frequencies is the number of students in the school. So I'm just going to divide that by the sum of the frequencies. And this gives me 15.9, which is what we calculated before. We're now going to move on and look at estimating the mean. So in a number of situations, you'll have data where you don't actually have the exact values, you just have them grouped up in such a way that you can see what category they fall into. So, suppose this is a bunch of, who knows, let's say pet dogs, and you've got their weights, but they're grouped up. Okay, we've got the 5 to 7 kilogram ones, and there are 3 of those. We've got 7 to 8 kilogram ones, and there's 11 of those, and so on. So how could we estimate the mean here? Well, if this is all the information we have, what we'll really need to do, it's hard to do better than just assuming that all of these data points are centered at the middle of these ranges. What I mean by that is we're just going to pretend that all 3 of these pet dogs had a weight of 6 because 6 is right in the middle of that group. And we're going to just pretend or assume that all of those 11 dogs had a weight of 7.5 and all 14 of these had a weight of 8.5 and so on. Really, we're not actually assuming that they all did have those weights. It's just we're assuming that their weights were spread evenly within that range. So what we do is we create a midpoint column where we write down all of the midpoints. So 9.5 is halfway between 9 and 10, 12.5 is halfway between 10 and 15, and so on. And then we just calculate the mean average using these frequencies and these midpoints. And so what we get in this case is this calculation. So here's our formula, and it's just frequency times midpoint plus frequency times midpoint plus frequency times midpoint, and so on. That's a sum of all of our data. And then we divide by the number of data points, which is, as before, is just the sum of the frequencies. And I'll show you this in Excel as well. So once we've got these midpoints, it's just our sum product function. And I'm selecting my frequencies and my midpoint values. And so this, if I just work this out, that's the sum, an estimate for the sum of the weights of all of my dogs. And then if I divide this by the sum of the frequencies, that's dividing by the number of terms in my sample. And I get 8.95 kilograms. Now I want to have a look at some potential issues. So suppose I had this data, and this data is on the amount of rain that fell over a few months. And so here I've got the frequencies, here I've got how many millimeters of rain it was, and I've got midpoints here because it's we're estimating because of the ranges. So what's the issue here? Well, look, I can calculate the mean, I can do it, and we get an average of 2.33 millimeters. Now, think about why this is potentially wrong, why it probably is. Well, you don't need to be a meteorologist. Is that someone who looks at weather? I think so. To understand that on many, many days, it does not rain at all, even here in the UK. So of these 96 days that we've got here, many of those will just be 0. So by treating this as a midpoint of 1, it's assuming that the data in this group was spread evenly between 0 and 2. There are some days with 0.1, some with 0.2, smoothly all the way up to 2 millimeters. Whereas in reality, an enormous number of these days probably will just have 0 rain. And so what we've probably done is ended up overestimating the mean by assuming that the midpoint of this data here, or at least that midpoint, was a good representation of these 96 days. In reality, we just don't know. Maybe on 90 of these 96 days, it didn't rain at all, in which case this one is very unrepresentative of the data. Maybe on half of them it didn't. Who knows? But what we do know, or at least it's reasonable to assume, is that rain is unlikely to be evenly distributed between 0 and 2 millimeters because there are so many days where it doesn't rain at all. So be careful of situations like that. If you've got group data, you do need to be careful that if you're using midpoints, that it's reasonable to think that the data could be spread evenly through that group. So that's one of the many issues which you might need to consider. Okay, so that's all for the mean now. I hope that's been a useful look at it, or maybe a refresher. In the next video, we look at the median. I'll see you there. Having looked at the mean average in the previous video, we're now going to look at the median, an alternative way of calculating an average. So the median average is the middle value once your data is arranged in order. So I've got the same set of numbers I had in the previous video here, and I've made sure they're definitely arranged in order, and I want the middle value. Now, if we have 7 data points, the middle value is the 4th one. It's 37. So that is the median value. Now, to see why it's that one, you could imagine crossing off the first one and the last one, the second first one and the second last one, and so on until you get that middle point there. So that's how we calculate the median in a really simple case. If you want a formula for this, and I don't suggest this is how you think about it, it would be this. The median is x sub n plus 1 over 2. So what on earth does that mean? Well, it means if n is your number of terms, so in our case 7, you do 7 plus 1, which is 8, divided that by 2, and it's 4. So that's x4, the 4th term in the data set. So that's a formula for calculating the median position. Now, this works if you have an odd number of data points as we do here, and also if you have an even. Let's have a look at when you have an even number of data points. So in this case, I've just got 6, and so the median position, well, the middle value, there isn't one, but there is a kind of midpoint here where we've got 3 data points on each side. When that's the case, you just find the value which is halfway between these two, and we just actually add them together and divide by 2. So it's actually calculating the mean average of those two. So the median here is 32 plus 37 over 2, which is 34.5. And again, the formula does work. We just have x sub 6 plus 1 over 2, so that's x sub 3.5, and x 3.5 is halfway between x3 and x4. So that's what the median is, and that's how we calculate it when we have a list of data. Now, you can do this in Excel, so let me show you how. So Excel has a median function. You just type in median, easy as that, select your data, and you get the median. And as we got before, it was 37. And then when we had 6 data points, Excel can do that as well. It's just equals median, select the data you want, and there we have it, 34.5. Okay, now just a word on notation. The median is variously known by a lot of different names. Sometimes it's referred to explicitly as the median, sometimes it's shortened to med. You'll sometimes see little m, capital M, and even Q2. Q2 refers to it's the second quartile, and we'll look at quartiles later on in this chapter. So just be aware that there are a range of different ways that it will be referred to. And yeah, a good statistician will just make it clear by saying explicitly that it is the median average. But just be aware there's not really a standard notation like there is for the mean. Okay, so let's have a look at estimating the median. So suppose that we are looking at the age data we had from before. So this is where we have 76 people who are 14 years old, 121 who are 15 years old, and so on. And we wanted to estimate the median age. Well, here's a way to visualize how we do this. So first imagine that we had all of the people, okay? All 300 and whatever of them. And we lined all of them up. And let's now divide them into their age groups. So we know that there are 76 14-year-olds, and we know that there are 121 15-year-olds, there are 118 16-year-olds, and there are 107 17-year-olds and 54 18-year-olds. So the first thing you do is say, well, where is the median? Well, the median of 476 students is the 238.5th. Okay, that's the middle position. So it'll be halfway between the 238th and the 239th. So our job, in a sense, is to locate the 238th and 239th student in the list and take the position halfway between those. So here's how we're going to do that. This is where the median is, let's say. So where is that? Well, it's going to be 41.5 into this range. And the reason for that is that 76 plus 121 leaves 41.5 remaining to get us up to 238.5. So 238.5th person is 41.5 people into that group. So then what we can say is what fraction of the way into that group are they? So that's just 41.5 over 118. There are 118 16-year-olds, and the 41.5th position in that group is going to be 41.5 over 118, that fraction of the way into that group. So what is that? That's 0.35. So if we assume that these 16-year-olds are evenly distributed from exactly, it's their 16th birthday, smoothly distributed all the way up to just before their 17th birthday, then it would be reasonable to assume that the median student is 0.35 years into being 16. And so 16.35 years is going to be a good estimate of the median age student. So that's one method. It's called linear interpolation, if you're interested, for how we can estimate a median. Now, of course, that's 16.35 years, and we might want to write that in months. So 16 years and 4 months, because 0.35 years is about 4 months. Finally, we're going to look at how this can go wrong. So why might we get a bad estimate using that kind of interpolation? So if I use that method on this data set here, so I find the midpoint and I do the method that I did in the previous slide, I end up with the 63rd place, which is the correct position of the median, being 1.3 millimeters, and that's my estimate for the median. Now, in the previous video, we discussed how, in this case, it is plausible at least that many of these days, the 0 to 2 millimeter days, were ones in which there was no rain at all. And so it's also plausible then that the 63rd day might have been a day with no rain. It might have been that 70 or 80 of these days with not very much rain had no rain, rather than 1.3. Basically, this is a context where it's probably wrong to assume that the 96 days were smoothly and evenly spread between 0 and 2. They probably weren't. They were probably bunched up at the 0 end. So we can only use that linear interpolation method if it's reasonable to assume that the data is spread evenly within these different class intervals. So be careful with that. If you're making an estimate, be aware of what you're assuming, and if it's no good, then you can't make that estimate, I'm afraid. So that's the median average, and in the next video we're going to look at the mode. We're now going to look at the third type of average, the mode, or the most common value. So let's have a look at this. So if we go back to these 6 numbers here, the mode is 32, and the reason why it's 32 is that is the only number that appears twice. It is the most commonly occurring number. So 30 just appears once, 37 appears once, 42 appears once, 50 appears once, but 32 appears twice. So it is the modal average, the mode average of that dataset. This dataset here, well, this one's got a mode of 50 because 50 appears twice in this one. And in this dataset, well, there are 2 modes because 32 appears twice and 50 appears twice as well. So that will be something we would call a bimodal dataset. Now, my suggestion to you is that the mode is not a very useful average to use in almost all circumstances. The reason is, okay, suppose I wanted to think about this data set here, where the mode has come out to be 50. Well, what is my average? What is an average supposed to tell me? It's supposed to tell me in some sense what a normal value is. It's supposed to be a representative value which tells me, which describes the data set. Now, finding out that the mode is 50 doesn't tell me nothing. It tells me that 50 occurred more than the others. But it's clearly not representative of the full data set here. It's fairly arbitrary which value appeared twice, right? This could have been a 49 and then we just wouldn't have had a mode. So for very small data sets, it's almost never an appropriate average to use. I want to show you the 3 circumstances in which the mode is a useful average. So the first one is if you have qualitative data. So if I ask a bunch of people what their favourite colour is and record the frequencies here, well, the most common answer was blue, and so in that sense, blue is the modal, it makes sense to say blue is the most common answer. That makes sense. I can't really do anything else. What would the average colour be? It doesn't quite make sense in the case of colours, and you certainly couldn't do any kind of adding up and dividing here. But you can clearly see that there was a most common answer. So in that sense, the mode works well for qualitative data. It also works well when you have a small number of options and lots of data. So take this data here from the UK about the number of cars owned per household. So 4.3 million households own 0 cars, 5.9 million households own 1 car, 2.6 million cars own 2, and so on. So in this case, the most common answer was 1, and in this case, I think that is a meaningful answer. The most common number of cars per household in the UK is 1. I've now learned something about UK households. Of course, I could find the mean average, or I could estimate the median as well. That's okay, and get a decimal number. Maybe the mean average is 1.4 or something, who knows. But the modal average makes sense here. Because I've got such a large data set, it becomes less arbitrary, right? If I just asked 3 households and it was 1, 1, and 2, and I got a mode of 1, that's not going to tell me quite so much. But if I've got an enormous sample size and restricted options, then that can tell me something meaningful. The final case in which the mode can be useful is if you have a distribution, a frequency distribution. So in this case, I've plotted a frequency distribution for house price and frequency. And you would expect it to have this kind of shape because there's going to be a kind of common, or at least a most common house price value in any particular country. There's a hard cutoff point at 0. A house can't cost less than 0, but there's no real upper bound here. A house can cost anything. So you can have a £20 million house. So these things do exist. You can have house prices that are way above the average, but not way less than the average. So in this situation, what's the modal house price? Well, the modal house price is just the top of the curve. So the mode is just the peak of a frequency distribution. Now we're going to talk about frequency distributions much later on in the course, but for now it's just a model that shows you how probable or how frequent different, well in this case house prices are. So an interesting thing to know is that when you've got a frequency distribution with this sort of shape, you tend to find that when the mode is the top of the curve, which it always is, the median is a little bit higher. Okay, if you've got this tail over here, it's called a positive skewed distribution, more on that in a future video, the median will be a little bit higher and the mean will be even higher still. And that's because the mean is distorted by very large numbers, right? A £20 million house affects the mean because the mean you add up all numbers and divide by the number of terms. It doesn't really affect the median, it doesn't affect the mode at all. So that's meaningful to know what the most common house price is when you've got a frequency distribution. That is meaningful. If we were to flip this round and look at a negatively skewed distribution, for example, life expectancy. So there's not a hard cutoff point, but almost no one lives beyond 110 years. And happily, mostly we live in a world in which the chance of dying very young is very small. And so what we end up with is this sort of distribution where the outliers or the large outliers are on the bottom. And it's very, very surprising when a young person dies. It's quite surprising when someone lives to 100, but no one lives to 120 or 130, really. So in this kind of distribution, we could say that the modal number of years to live will just be the top of that curve, whatever that number is. There will be a median, which will be slightly less, and there will be a mean as well, which is slightly smaller again. So this is a pattern which we'll explore more when we look at skew. So the pattern that we generally see then is that modes are a bit less than medians, which tend to be a bit less than means when our data is distributed like this, sort of clustered on the small values with a few big outliers at the top end. And the reverse is true when our data, like life expectancy, has outliers at the smaller end. The mean tends to be the smallest, then the median, then the mode. A little challenge for you, if you're up for it, could you find a set of numbers of any size where the median is less than the mean, which is less than the mode? Or where the mean is less than the mode, which is less than the median? See if you can find any set of numbers that meets those two conditions. So we've now looked at the mean, the median, and the mode. And in the next video, we're going to look at when to use each one, what are the limitations of each, and how you can think carefully about which one to use. I'll see you there. Having looked at all three common measures of averages, we're now going to think about the differences between them and when to use each and what the pitfalls are of each of them. Okay, so you've got some data of house prices. You've got 5 houses on a street and you want to analyze this data. So which average do you use? Well, here's the mean, the median, and the mode. So what we can see from this is that the mean and the median don't differ by very much. Now, the mode, as we discussed previously, when you've got a small sample size, the mode is very rarely representative. It's just completely arbitrary that 2 of the houses happen to be 380,000. This one could have been 381 and suddenly that wouldn't have been the mode. So we're going to rule that out. That's not a good one to use in this case. But mean or median, well, in this case, take your fancy. But what about if one of the houses was knocked down and replaced by a $1 million+ mansion? What happens to our figures then? Well, the mean has shot up to 500,000. The median is still 330,000, though is no longer a mode. So in this case, which one do we prefer? Well, remember what the average is supposed to achieve. It's supposed to be a representative value that gives you a sense of what a normal house price would be. Now, I think it's clear to me that 500,000 isn't really representative of any of them. It's substantially more than all of these, and it's much less than this one. So the mean has been artificially inflated by this single large outlier. This is a theme that we'll be coming back to a few times in this chapter. The median, on the other hand, remains the same and remains fairly reflective of these four houses. So it does a reasonably good job. So this is something which you should bear in mind. The median is resilient to single or a small number of large outliers in a way that the mean isn't. So when you have big outliers or sometimes very small outliers, you've got to be careful about using the mean. You can end up with a value which is not really representative of what an average should be representing. Now, there are a bunch of situations where it really doesn't matter which average you use, at least between the mean and the median. So take these three distributions. All of them are symmetrical, and symmetrical distributions have the property that the mean and the median will always lie right in the middle of the distribution. Now, even if it's a weird shape like this, the mean and the median will always lie right in the middle. So in these kind of distributions, it doesn't matter if you use the mean or the median. However, as we saw in the previous video, when you have a skewed distribution, like income, for example, it does matter which one you use. So income is skewed because there is a fixed hard limit at this end. You can't earn less than 0, but there's no upper bound. Okay, you can earn 10 million a year more than the average. So in these kind of situations, as we saw before, the mode is the top of the curve. The median gets pulled up a little bit and the mean gets pulled up a lot. So if your data is too skewed, the mean sometimes stops being representative of the whole. In the case of income, right, a single outlier can just drag the mean up a lot. Like if one person whose income is $1 billion a year walks into your data set, into your sample, the mean will shoot up. So single outliers have an oversized effect on the mean, but not on the median. Here are some figures I found for the United States. At the time of recording, the median income is $34,000 a year and the mean income is $52,000 per year. So there's an enormous difference between these. Remember, the median means that half of all people who earn a salary in the United States earn less than $34,000 and half earn more. So this mean average is substantially more than what most people in the States earn, and therefore is not particularly representative. And that's because we're dealing with a distribution that has big outliers. Let's consider a situation that proves that there's not always a right answer of which one to use. Suppose that we were investigating crime across 5 districts in a city. So in year 1, these are the number of crimes that occur in these different districts, and then this is what it is in year 2. And we can crunch the numbers and we can work out that the mean average has gone up by 10, but the median has gone down. Now, has crime got worse or better? I mean, if you look through the numbers, what's happened? We've got crime has gone up by a lot in District A, it's gone up by quite a lot in District B, it's gone down by a little bit in C, down by a little bit in D, and up by a lot in E. So I guess the reason why the median has fallen down is because of these little changes in some of the middle values here. Has crime got worse? Well, the mean certainly suggests that there's been more of it. So you can see it's kind of hard sometimes to make sense when you just see these figures. It's hard to know which one is telling the truer story, and I'm not sure that always is. Consider this, for example. Here's year 3. Well, in year 3, what's happened? Well, both the mean and the median have gone up. Investigating this further, well, crime fell in District A, it fell in District B, it went up significantly in C, it fell in D, and it fell in E. So, I mean, a politician might claim, and the mayor of this town might claim, that crime fell in 4 out of 5 of the districts in this city between these 2 years, which sounds positive, and yet the mean and the median have both gone up. Do both of these give a true reflection of what's happening in the city? Not really. You need to look at the numbers, right? Only look at the numbers, you would see that, well, things seem to have improved for 80% of the residents. It's just in one district, it's got much worse. All of this is to say, there isn't always an answer about which of your averages is the right one to use. Sometimes you need to get your hands dirty and actually look at the numbers yourself. Okay, actually look at them and not just the descriptions, not just the averages. Anyway, I hope that's been a useful look at the differences between means, medians, and modes. And we'll just finish with some questions for you to ask of yourself. So this first question is really for you if you are working in a business, if you ever use numbers in your work, or even if you're a student, you may come across this sort of thing. Are there areas of your work in which you are presented with averages? Maybe not, but if there are, what are they? Do you know which average was used? So the last time you were presented with an average, do you actually know whether it was mean, median, or mode? I think a lot of times we're just told averages and we don't actually know which one was used. And as we've seen over the last few videos, you get very different answers depending on which one you work out. You really need to know which average you're being shown. Also, if you have been shown an average, was it the most appropriate one being used? Maybe you were shown the mean average of some data that actually on reflection should have been treated with the median. Or maybe you're shown the mode and it wasn't very meaningful. So think about whether the last time you saw an average being used, apart from this video, was it the most appropriate one? And finally, might there be areas in which averages are disguising a more nuanced story? As you saw from that case with crime rates in the city, you can sometimes disguise more than you can reveal with averages. So have a think about the times that you've been exposed to averages and ask whether you think digging into the data might have actually revealed something more interesting. I hope this has been a useful look at averages. We're going to move on to spread of data in the next few videos. I'll see you there. We're now going to look at some measures of spread, starting with quantiles range and the interquartile range. So quantiles are measures of location in ordered data. And I'm going to show you the 3 most common types of quantiles. So the first one we're going to look at are quartiles, which, as the name suggests, are locations 1/4, 2/4, and 3/4 of the way through your data. We're then also going to look at deciles, where your data is split into tenths, and percentiles, where it's split into hundredths or percentages. So let's start by looking at quartiles. So suppose that you had this group of people arranged by age, and you wanted to find their quartiles. Here's how you'd go about doing it. You first identify the median, so the person who is right in the middle. We can even take a note of that. So the median age of this group of people is 41. Then you look at the left-hand side, so all of the people to the left, or with ages that are smaller than the median, and you find the median of that group. So it's this person here in the middle. So that is called the first quartile, or Q1, and it's 29 years in this case. So the quartiles mark the quarter points through your data. So the first quartile, or the position which is 1/4 of the way through your data, is 29 years. If you want to find the upper quartile, you just consider exactly the same thing on the right-hand side. So you're looking at everyone whose age is greater than the median, and the middle of that group, so the median of the people on the right-hand side, well, that person there, their age is the upper quartile, which we call Q3. Now, you might wonder where Q2 is. Well, we sometimes call the median Q2, but I'm just going to leave it as the median today. So Q1 and Q3 are the lower and the upper quartiles, respectively. Now, it's common when we've listed out the quartiles to also include the minimum and the maximum. So the minimum age is 23 and the maximum age is 62. So those 5 points, the minimum, the lower quartile, the median, the upper quartile, and the maximum, are 5 really important data points, which, as you'll see when we look at box plots later on in the course, are important kind of positions in your data set, which tell you a lot about it. Okay, over to Excel now to see how we do it there. So here are our ages, and to find the quartiles, we just use the Excel function quartile dot exe. It's an exclusive quartile function. I'll explain to you what the inclusive one is in a moment, but the calculation that we made previously was using this one. So you highlight your data, and then you say which quartile you want. So there's the option for first quartile, so 25th percentile, 25% of the way through your data, the median, halfway through, or the third quartile, the upper quartile. And so we just say 1 if we want the first quartile or the lower quartile, and that's 21, which is what we got as well. So that is Q1. And Q2, well, Q2 we could either find using the median function, which we've done previously, 41, or we could use the quartile function. So quartile, and it's the exclusive one. You select your data, and we want quartile number 2. And if you want the upper quartile, Q3, it's the same thing again. We want the quartile function, select your data, and it's Q3. Now, if you wanted your minimum and maximum as well, you can get those, and those are pretty easy in Excel because the functions are just min and max. So you type in min, select your data, and it gives you the minimum, and then the same thing for maximum, it's just max, open bracket, and then you select your data, and there it is. All right, so what is Excel talking about when it talks about exclusive quartiles or inclusive quartiles? Let me show you. Previously, we worked out the lower quartile like this. We looked at all of the data points that were less than the median, so all of the people younger than the median value, and we found the median of that group, excluding this middle point, so excluding this person in the middle. So the inclusive function is just if we include that. This is a less standard way of calculating the median, but you'll sometimes see it. So if you ever see someone refer to an inclusive quartile, it's because the median was included when we looked at this lower group of ages. Then we would just need to find the median of this group. Now, because there are 6 terms, the median position is halfway between the 3rd and the 4th place. So that's a number halfway between 29 and 33. So our lower quartile goes from 29 up to 31 if we use the inclusive function. And similarly, we can look at the right-hand side, and if we include the median there, well then our upper quartile is halfway between 50 and 56. So rather than 56, it becomes 53. So that's what the inclusive function means. Let's now have a look at some other quantiles, starting with deciles. Okay, so deciles are the positions which are tenths of the way through your data. So if I have a bunch of data here, and here is one data point, if that is D6, decile 6, it means it is 6/10 of the way through my data. Think of that as being 60% of the way through your data, or 6/10. So D6, decile 6, tells us that that's the position of that data point. This point here, well, if that turns out to be D2, it means that is 2/10 of the way through your data. So deciles are no harder than that, just tenths. What about percentiles? Well, if this position here is P74, that's percentile 74, it means it is 74 hundredths or 74% of the way into your ordered list of data. Similarly, if this point down here is P12, it tells you it's 12% of the way through your data. Now, just a warning, you'll often hear people say things like, a bunch of people did a test, and this person, well, their score was in the 95th percentile. Now, what do they mean by that? Well, the 95th percentile is the position, which is 95% of the way through your data. So technically, the 95th percentile is that point, but in a kind of non-technical way, when people say in the 95th percentile, they are not referring to that position, they're referring to that group. So the 95th percentile would represent the top 5%. So just watch out for that. When people refer to something being in the 95th percentile, they're talking about that kind of range beyond, including and beyond the 95th percentile. Similarly, if they say, their IQ is in the 99th percentile, what they mean by that is that, it's in the top 1%. So now that we've got these position metrics of quantiles, we can look at how we use them to measure spread of data. So we're going to begin by looking at range and interquartile range. So ranges are pretty simple one. Let's have a look at this data here. So I've got the data from two companies, the profits from two companies measured in thousands across 7 years. So, okay, I've gerrymandered the data so that they have the same mean and median. So if we only looked at averages, we wouldn't really be able to tell apart these two companies because it's the same for mean and same for median. Both of them have an average profit of $49,000 per year. But if we look at the data, there does seem to be a difference. So one difference that I can spot is that the data for company A seems to be more spread out. I've got values down in the 30s and values up in the 60s. And unlike that, in company B, it's all in the 40s and 50s. It's really high 40s and low 50s. So it seems to be much less spread out. So it's a measure of range that can capture that difference. So here is one way that we can do it. The range is a very, very simple measurement, which simply takes the maximum value and subtracts the minimum value. So for company A, the max was 69 and the min was 32. And so company A has a range of 37. Obviously, our units are thousands, so that's $37,000. B has a max value of 53 and a min of 44. And so that would be a range of $9,000. So super simple, also pretty crude and not always that helpful because the entire metric depends just on two values, which isn't that sophisticated. Nevertheless, it's not meaningless. It tells you across which range the results are spread. A more sophisticated measure of spread is the interquartile range. So what I've done here is I've calculated Q1, Q2, that's the median, remember, and Q3 for company A and company B. Now, the definition of the interquartile range is simply the upper quartile minus the lower quartile. So for company A, that's 63, the upper quartile, minus 34, that's the lower quartile, and that gives us 29. So the interquartile range, that's the range between the quartiles, is 29,000, whereas for B, it's 52, the upper quartile, minus 45, the lower quartile, which is 7. Now, what does the interquartile range tell us intuitively? Well, it tells us where the central 50% of your data is. Okay, it tells you if your data is spread out across this range, it tells you where the central 50% is. So it's a really good indicator of where the standard results in your data lie, where the most common results will be. And for that reason, it's a pretty useful measure and it's quite resilient because if you have single enormous outliers, they're not included in it, which is a strength and a weakness. More on that later. But yeah, very commonly used measure of spread. We've also got a really nice way of displaying interquartile ranges visually. So take a look at this. What I've done here is I've plotted what's called a box and whisker plot or a box plot. I'll cover this more later on in this course. And what these two boxes and these whiskers show is, well, let's have a look. For company A, it shows us the minimum value down here. Minimum value, what was that? The minimum value was 32. So It has a minimum value of 32 here, and then this box here runs from Q1 up to Q3, and there's a line in the middle for the median. So the width of this box, or the height of this box really, represents the interquartile range, and then you've got the maximum value up here. Now for the orange box, that's company B, you can see that the interquartile range running from the lower quartile to the upper quartile is much smaller. So visually you can just compare interquartile ranges really easily using these box and whisker plots. Let me show you how to do that on Excel. So super simple, here's the data. All you need to do for this is select all the data that you want included, and we're going to insert, well, it's a statistics chart and it's box and whisker. So here we go. We can get rid of the chart title if we don't, or we could add one if we wanted. Okay, it's mislabeled that, don't worry about that. And then if we want to change the range here, we can double click on this axis here. And rather than going, for example, from 0 to 80, we might want this to just go from 30 to 70, for example, so that the data is displayed a little bit more clearly. So yeah, really easy to do in Excel, and yeah, we'll look at that more later on in the course. So that's it for quantiles, quartiles, range, interquartile range, that sort of thing. We'll be referring back to these measures over and over and over again. So do watch the video again if you need a reminder of how to do it. In the next video, we're moving on to more complicated, more sophisticated measures of spread. I'll see you there. We're now going to look at a more sophisticated measure of spread, and that is standard deviation and a closely related concept, variance. So rather than launching straight into definition, formula, and application of standard deviation, we're going to take a little bit of a run-up to this concept. So imagine that you had some data points, which I've spread across a line to show how they are spread out here. Well, here are the upper and lower quartiles, just 1/4 and 3/4 of the way through the data. Now notice that if I changed the data, if I moved some of the points around like this, but I kept the quartiles the same, well then the interquartile range hasn't changed because the quartiles didn't move. Just to show you again, here's the original data, and here it is when I've changed it. Now, the interquartile range would be the same for these two data sets. But clearly there is a difference between the spread of data in each. Most people's intuition would be that this data is much more spread out than this data, but the interquartile range is not capturing that fact. So this is where a measure like the standard deviation can come in, because it can capture our intuition that these data sets are different, and unlike the interquartile range, it takes note of every single data point. Every single data point contributes at least something to the measure. Now, I'm actually going to show you something which is not the standard deviation first. I told you we're taking a bit of a run up to this because I think it highlights intuitively what the standard deviation is measuring, but it is different from the standard deviation. So let me show you. So suppose I wanted to measure how spread out this data was. Here's one way I could do it. I could measure the location of the mean, and then I could measure how far each data point was from that mean. Here's what I mean by that. Here's the distance of the most distant point, this point here, to the mean. I could take note of what that distance was. And then I could measure the distance of that point to the mean, that point to the mean, that one, and so on. I could do this for each of my points and then take the average of those. And that would give me an average distance to the mean from each of my points. So let's have a look at that in practice. Let's just look at company A's data. So this is their profit in thousands per year. So I've calculated the mean, it's 49. So what I could do then is I could take what's called the absolute deviation. So that is how far each point is from the mean. So 32 is 17 away from the mean because 49 minus 32 is 17. And 49 is 0 away from the mean, and 44 is 5 away from the mean, and so on. 52 is 3 away from the mean. They're all positive, it doesn't matter whether they're above or below, so hence absolute deviation. And then I could just take the average of these, and I get 10.6, and a formula for this would be to add up all of those differences with the modulus sign to make sure it's the absolute value, so just the positive one, add them all up and divide by the number of terms, and I get 10.6. So this here is not the standard deviation, it's actually called the mean absolute deviation. And what does it measure? It measures the average distance to the mean. And it's a very intuitive measure that we might come up with. It's also not really the measure which is used in, I'd say, 99.99% of all statistical analysis. What's used is a similar concept called the standard deviation. The reason why I show you this, though, is that the mean absolute deviation gives you a bit of an intuitive sense of what the standard deviation is almost doing. So what's the standard deviation? What's the thing that everyone uses? Well, I'm just going to throw you in at the deep end and show you not just one, but two different formulas. We have one formula here when we're dealing with population data. So if you happen to have all the data in a population, remember our definition of population, it's just all elements in the set that we're interested in studying. And then a slightly different formula if we're dealing with a sample. Now, I really am not interested in getting too far into the difference between these. I will explain some of it to you. But essentially, this one here is a good estimate of what the standard deviation for the population is when you're just working with a sample. So let's investigate what's happening in this formula. The key thing is, rather than adding up the absolute differences and just dividing by the number of terms, we're adding up the squared differences. So we're taking the gap between each data point and the mean, and we're squaring it. We're then taking the average squared distance by dividing by, well, n if it's the population and almost n minus 1 if it's a sample. So it's almost the average squared difference here. And then we're square rooting our answer. So we'll work through an example and then we'll talk a little bit more about why it's n minus 1 for a sample. As I've said previously, you're almost always working with a sample, so it's usually this formula you'll be working with. So let's take a look at an example. So here's company A's data and here's the mean, 49. So how do we work out standard deviation? Well, we do the following. We look at the difference between each of our data points and the mean and we square it. So the difference between 32 and the average 49 was 17, so we square that and we get 289. The difference between 49 and the mean of 49 was 0, 0 squared is 0, and so on. The difference between 44 and the mean was 5, and we square that, and so on. And then we take all of these differences here, we add them up, and we divide by n minus 1. So we add them up to get 1,144, and we divide by 7 minus 1 because there were 7 minus 1. So there were 7 data points, so we're dividing by 6. We calculate that and then we square root it and we get 13.8. So it's similar, but not exactly the same as the mean absolute deviation, but you should still think of it as, so it's similar, but not exactly the same as the mean absolute deviation. But you should really intuitively think of it as something like that. It's showing you a pretty common distance to be from the mean. What I learned from this 13.8 figure is that it's pretty common to have a profit which is within about $13.8 thousand of the mean. So that's the kind of intuitive understanding of that. We can do this in Excel as well, really easily. The function that we need here is stdev, so standard deviation. Now we've got two options here. We've got stdev.p and stdev.s. So that's the standard deviation based on the population, if you have the entire population, or the standard deviation based on a sample. So we are basing this on a sample. This will pretty much always be the one that you use unless you are certain that you have all the data that exists. So I just select that and out it comes, 13.8. If we were going to calculate or use the population version, you'll see that it is small, and that's the kind of underestimate idea, that it's underestimated how big the standard deviation is. Now, it's worth saying, that really may be all of the data for company A in those years, but by population we mean all of the data, all of theoretically possible amounts of profit that company A could have made. So it's kind of trying to work out what an underlying distribution might have been. We definitely don't have that in this case, and so I'm going to get rid of that, and it's the stdev.s formula, so the sample formula that we use in Excel. Now, I do want to show you a little bit about why we divide by n-1 when it's a sample, because that's the formula we're using in most situations, because we usually don't have full population data. So here's why. So suppose that I've got the mean of my samples. Here's a sample taken from a population. So since at the heart of the formula are these distances to the mean, here's the idea. The population mean might not have been exactly there. This is just the mean of my sample. Population mean might have been over here, or it might have been over here, or it could have been anywhere, right? Well, not, yeah, it could have been anywhere. The most likely place for it to be is here, but it might have been in any of these places. Now, taking measurements from my sample mean, like this, builds into the function something which minimizes the distances. Now, had the population mean, been anywhere else, then all of these squared distances would have been more. So my sample mean has biased my calculation to be a small calculation because the formula bases itself around the central point of the sample itself. So it's artificially made the standard deviation a little bit too small. Now, the correction factor for that is rather than dividing by n, we divide by n-1, because when you divide by something a little bit smaller, your result is a little bit bigger. Now, as for why that makes the correct adjustment, that's well beyond the scope of this course, but it has to do with something called moments, which I will talk a little bit about in the next video. So, a very kind of brief intuitive explanation for why it's n-1 and not n is that our sample mean situates itself right in the middle of all of our data and hence artificially minimizes the distances compared to what they might have been had the population mean been somewhere else. Okay, so all you really need to take from this are two things. One is you should think about it as a common distance from the mean. It tells you roughly how far your data is from the mean, and that it's based on squared distances. That has a sting in the tail because it means that if you have any big outliers, when you take those outliers, find their distance from the mean, which is going to be big because they're an outlier, and you square it, it gets very big. So standard deviations are strongly impacted by outliers. Okay, let's now have a quick look at variance. So variance is a pretty simple thing to explain. It is simply the standard deviation but without the square root on it. So it is the standard deviation squared. Now, why do we care about variance? Mostly we don't. We just use it a lot for two reasons. First reason is it's a bit easier to use than standard deviation because it doesn't have the square root, so it's easier to combine with other things algebraically. And then secondly, it's because it's related to a whole family of calculations based on squares, cubes, fourth powers, fifth powers called moments, which I'll look at in the next video. But it is referred to quite a lot, even though it's not that intuitive. Let's just take a look at this example here. So suppose I had the price of a bunch of different products or something, or maybe different prices for the same products, and I wanted to calculate the variance, I'm just taking the distance to the mean in each case, squaring it, adding that up and dividing by n-1, but not square rooting it at the end. Now, the answer I get there is 59.7, which is not an intuitive number. It's the square of the standard deviation. So the square root of this, around 7.5, would tell you that most of my data is within $7.50 of the mean. This doesn't tell me anything intuitively, really. And the units are weird because the units are squared as well. Since my original units were dollars, the units of my variance are dollars squared. So that's how you calculate variance. It's very easy. Just be aware that it doesn't mean very much intuitively. It's the square of something that is intuitive, and that its units are also squared. We can work it out on Excel very easily. So all we need to do is type in equals, and then the function we want is var for variance. And okay, we have the option as before of var.p, so that's if you happen to have the entire population, which we almost always don't, so we're going for var.s, that's the variance based on a sample. And all we need to do is select our data here, and that calculates our variance, which we got to be $59.7 squared. Finally, just a note on notation. So the standard way to represent these is with these letters. So for standard deviation, if it's a full population that you're working with, it's often sigma, Greek lowercase sigma. If it's a sample, it's a lowercase s. Variance, well, it's just those things squared. If you see sigma squared, that is the variance for a population. If you see s squared, that is for a sample. And to distinguish between different data sets, you'll sometimes see a subscript used. So for example, it's pretty common to see something like sigma x with a little sub x if that's the standard deviation of your x data set, or sigma y if you're dealing with your y data set. Similarly, you might see s x as the standard deviation for sample standard deviation for a data set x, or s q if it's the sample standard deviation for data set q, and so on. And you can also have subscripts for variance as well. You'll see things like sigma squared m if it's the variance for your data set m, and so on. So these are the ways that we refer to variance. It's with these letters. Okay, that's all for standard deviation and variance. I'll see you in the next video. We're now going to look at a really clever and slightly more sophisticated measure of spread, the coefficient of variation. So here's why we need the coefficient of variation. Suppose I've got these two data sets, 10, 20, 30, and 110, 120, and 130. Now, in some sense, these are precisely as spread out as each other, because one of them is just 100 more than the other. And that's obviously what we get if we calculate the sample standard deviation. It's 10 in both cases. But that doesn't really capture it, because as a percentage of what the values are, the data in A are much more spread out. I mean, the highest value is 3 times as big as the smallest value. Compare that to data set B, where the highest value is just a few percent more than the lowest value. So as a percentage of their actual size, A is more spread out. So we can introduce something called the coefficient of variation, sometimes referred to as CV here. And the coefficient of variation is defined to be the sample standard deviation divided by the sample mean. So it's expressing the standard deviation as a fraction of the average. So it tells you how big the standard deviation is relative to the size of your data set. When we do this for A, we get 10, the sample standard deviation, divided by the mean of 20, so that's 0.5. But for B, we get 10 divided by 120, which is 0.08. So intuitively, that tells me that the standard deviation in A is 50%, 0.5, 50% of the mean. And for B, the standard deviation is only 8% of the mean. So it's a pretty useful measure to see how much things are spread out relative to their own size. Let's apply this to cryptocurrency. So I've got cryptocurrency data here from each month. The value of Bitcoin and Ethereum, I think at the start of each month through 2021. So these are obviously famously volatile commodities, and we could measure their standard deviation to try to get a sense of that. The standard deviation for Bitcoin is $9,650, and for Ethereum, it's $1,045. Now, that might make you think that Bitcoin was the more volatile cryptocurrency, but of course, we would expect a larger standard deviation because the value of Bitcoin is just more than the value of Ethereum. So you can see here, just it is worth more. So what we really want to know is how does this compare to the average? Is a variation, is a standard deviation of nearly £10,000 a lot or not very much given the value of Bitcoin? And it's the coefficient of variation which does this for us. So for Bitcoin, these are the measures that we can use, the standard deviation and the average, and for Ethereum, standard deviation average. And when we calculate the coefficient of variation, for Bitcoin, we get 0.21. So the standard deviation is 21% of the mean. Whereas for Ethereum, it's 0.37, so 37% of the mean. And then what that tells you is that Ethereum is more volatile. So coefficient of variation is a good measure of volatility. It tells us that relative to its own size, Ethereum is varying more than Bitcoin. Let's see how we do all of this in Excel as usual. So the measures that we're going to need are the mean and the standard deviation. So for Bitcoin, that is simply the average of these numbers, and I can just drag this across here to get the average for Ethereum. And then for standard deviation, we're just using the standard deviation based on the sample. And then I'll drag that over here to get the standard deviation there. Okay, so coefficient of variation is simply the standard deviation divided by the mean in each case. So there's our 0.205, which if I express it as a percentage, that's 21%. And the same thing we can do over here to get 37% there. So hopefully that's been a useful look at this alternative measure of volatility, the coefficient of variation. Remember, if you've only been told the standard deviation of two data sets on their own, that doesn't tell you how variable they are until you know the mean as well, and coefficient of variation is a pretty good way to tell you the relative size of the standard deviation. The next two videos are going to be the most technical ones of this chapter. We're going to be looking at skew and kurtosis, two pretty advanced descriptive statistics. So far, we've looked at averages and we've looked at spread, and we've also combined those with the coefficient of variation. But skew tells us about the shape of. So far, we've looked at averages and we've looked at spread, and we've also looked at the coefficient of friction, which combines the two. Skew describes the shape of a distribution. It tells you how your data is distributed, where it's clumped, where it's more spread out. Let me show you what that means. So here are a bunch of people with their ages. They're organized in ascending order. Now, the first thing I want you to do is just look through those numbers and see if you could find a way to describe this data set which isn't really referring to averages or spread. Well, one thing you might notice is that these are very much centered around the lower end. What I mean by that is about half of all of the people are in their 20s. You've got a few people in their 30s, 3 in their 40s, 1 in their 50s, 1 in their 60s. So the data is clumped around the lower end, right? Almost all of the data is young people, and then we've got a few outliers here up at the top. end. So we could group these into a frequency table like this, where what this says is I've got 4 people between the age of 20 and 24, 6 people in the 25 to 29 group, 5 people in their 30s, 3 in their 40s, and 2 in their 50s or 60s. And I could plot a histogram. We'll look at histograms more later on in the course, but this is just plotting what's called frequency density here against age. And it gives you a sense of the shape of the data set. We can see that it is clustered around these younger ages with a smaller group of people at the top end, the older people here. And we could smooth this out as well. You could imagine I might do the same thing with 1,000,000 people, have a very, very, very detailed histogram. And when I smooth it out, it might have this sort of shape here. So in this distribution, what we have is a mode. So that mode is the kind of top of the curve. We can calculate a median. So I calculated a median for the ages of our people and a mean. And this is what we'd call a positive skew. When you have data which is clustered around the lower values, where the outliers, the tail of the distribution as it's called, is on the higher end, that is called a positive skew. So think about it in this way. Positive skew is where the tail points in the positive direction. And a key feature of a positive skew distribution is one in which the mode is less than the median, which is less than the mean, as we discussed in an earlier video as well. So we'll always see this when we have a positive skew, that the mode, top of the curve is here, median a little bit higher, and the mean higher still, and that's because the mean is influenced by outliers. So remember that the one person who was in their 60s had no effect on the median, because, I mean, you could have changed that person to a 1,000-year-old and it wouldn't have affected the median or the mode, but it does affect the mean. So if your outliers are on the positive end, it drags the mean out this way. So that's a positive skew. Now let's look at what different skews look like. A negative skew just is the mirror image of that. It's where your outliers, your tail that is, points in the negative direction. And of course, that has the reverse property, which is that the mean is the smallest, then the median, and the mode tends to be the largest. And we can also have plenty of data sets that have no skew at all. So a classic one would be a bell curve of the normal distribution. Any symmetrical distribution has no skew. Okay, I want to show you how we can calculate skew now. So there is a formula and it gives you a number, and I'll tell you how to interpret that number. In order to do this, I need to talk to you about something called moments. I'm not doing this to freak you out or to impress you or because the formulas are beautiful. I'm doing it all because you actually need to use them. You don't need to use these formulas. Calculators and Excel and software does this for you. I'm showing this to you so that you can see the formula, so you can see why certain issues might arise in the use of these formulas. So do not be freaked out by all of the algebra here. I'm going to point out exactly what the key features are and how that matters to you. So let's build this up. The first moment is defined to be this. It is just the sum of your data divided by n. Do you recognize what it is? I hope so. It is the mean. So the first moment is just the mean average. How about this? The second moment is just the sum of the squares divided by n. So that's the average square value. And the third moment, well, the third moment is the sum of the cubes over n. So it's the average cube, and so on. You can have any moment you like. The 10th moment will be the sum of the 10th powers divided by n, the average 10th power. So those are moments. What's more interesting are what are called the central moments. So take a look at this. This is the second central moment. What's the difference between that and the second moment? Here's the second moment, here's the second central second moment, and it's just, rather than the sum of the squares, it's the sum of the terms minus the mean squared. Now, you might recognize that as well. That's basically the variance. it was a divide by n-1, but this is a variance if you have population data. So what's the intuitive understanding of this? This is the contribution of the second moment over and above what's already been taken care of by the mean. So by subtracting the mean here, we're basically saying what do the squares do that the mean hasn't already accounted for. And as I said, the technical understanding of this is not what matters. I just want you to see these formulas so that you know what the potential issues are. I will explain all. Well, what about the third one? It's often called the third standardized moment. Well, it's the same idea. We're taking the difference between each point and the mean. So we've now factored in the contribution of the mean. So we've kind of removed what the mean does. And we've also divided through by the standard deviation cubed. Again, not interesting why we do that. Key thing is the third standardized moment is based on cubes, and it's basically what the cubes do over and above what the squares and the unsquared terms do. And that is skew. Okay, this is a formula for skew. One final thing to show you, which is, okay, remember it's n-1 when we're dealing with a sample rather than a population, which we usually are. And similarly for skew, we've got this beast of an equation when we're dealing with a sample, which we usually are. For the 100th time, you don't need to remember this. This is not important. This is what computers are for. But the key thing I want you to notice is that this is based on cubes. What does that mean? It means if you happen to have an outlier, then that outlier will have an enormous contribution to the skew. Because if you have a single outlier which is far away from the mean, when you cube that, it's going to become enormous. If you have a data point which is very close to the mean, well, when you subtract the mean from your data point and cube it, I mean, it might even become smaller. If your distance to the mean is less than 1 and you cube it, it's going to shrink. So key idea here is that the formula for skew is based on cubes. And because it's based on cubes, outliers have a really big effect because you're taking a distance to the mean and you're cubing it. So if your distance was 10 and you cube that, you get 1,000. So that's the formula for skew. You don't need to remember that. You just need to know that that's what's going on under the bonnet. So you see what the formula is, and that formula is going to spit out a number. It'll be a number between -infinity and infinity, so just a number. And if that number is 0 or close to 0, it means your data has very little skew or no skew, and it will be close to symmetrical. It won't necessarily look like a bell curve, but a bell curve is an example of a symmetric distribution. If it's positive, it means it has positive skew. So if you've got a skew of 1.5, it might mean that your data looks like this with that positive skew shape. And similarly, if you've got a score of -0.8, for example, then it maybe looks like this with a slight negative skew. Of course, it could be much bigger numbers. You could have a skew of 100 if it's extremely skewed, or -50 if it's extremely negative skewed. But that's the skewness scale. Let's look through an example again. So here's the data that we had in the previous video with Bitcoin and Ethereum prices through 2021. If I calculate the skew of these, I get that Bitcoin has a skew of 0.14 and Ethereum has a skew of 0.24. Let me show you how you do that in Excel. So it's as simple as using their built-in skew function, which is just skew. So the skew for Bitcoin is 0.14 and the skew for Ethereum, I'll just drag this over, it will do the same thing, is 0.24. Now notice they do also have a skew.p function. So that is if you happen to have the population data, which we very rarely do, and you can see that's smaller. So that's the same issue as always, which is it slightly underestimates. So we're using the built-in skew function. So now you know what skew is and what the formula is, how are you going to use it? Well, if you have a large data set and you calculate skew and you get a really big number, like a skew of 10 or 20, or -10 or -20 or -100, it tells you that lurking in your data, there is a big outlier or big outliers. So it can be really useful when you've got a data set which is too large to just sift through by eye or not easy to graph. You can calculate skew, and if you get a big number, by big, I guess I just mean bigger than 3 or bigger than 5 or smaller than -5, that sort of thing, but sometimes very big indeed, like 50 or 100 or 1,000, it tells you that there are outliers lurking. And if there are outliers lurking, they could affect your other data, like they could be dragging the mean up or the mean down or the standard deviation. So skew is a great thing for telling you what the shape of your data is and alerting you to the presence of outliers. Hope that's been useful. In the next video, we get even more technical and we look at kurtosis. See you there. So having looked at skew, we're now going to look at kurtosis. This is the most technical video of this chapter. So statistical seatbelts on. So kurtosis is an interesting, quite complex, but useful descriptive statistic that was invented to help us describe the difference between this distribution, which you can see, and this distribution. So it's possible to have data sets which have the same mean, standard deviation, and skew, but clearly are different. So these clearly have the same mean because they're symmetric, and so their mean is in the middle, and they're both have a middle in the same point. I've constructed them so they have the same standard deviation of 6, and they both have a skew of 0 because they are symmetric. But they're clearly different. This yellow distribution has more of its data clustered in the center and in its tails, the bits over here, and less in what are called the shoulders of the distribution. Now, what's interesting is that until about 2014, people thought that kurtosis, which I'll unpack in this video, was measuring what they call peakedness. It's like how much do these peaks jut out? But it's not actually measuring that at all. It's all about how fat the tails are. So a fat tail is the events which are a long way away from the mean. It's about what impact those have. So a fat tail does not necessarily mean that outliers are more likely. It just means that when they occur, they have a bigger impact. So the tails can be on both ends, and a fat tail is where those large outlier events have a bigger impact. So we looked at this in the previous video, and I'm going to emphasize yet again that you do not need to know these formulas. It's just good to know the key elements of each one. So we saw the key element of skew is that it's based on cubes, and so outliers have a really big effect on that. So here's the fourth standardized moment. This is kurtosis, and it is based on fourth powers. So you take the difference between each point and the mean and you raise that to power 4. So outliers really have a massive effect on this. In fact, kurtosis in some ways is basically an outlier detector. When kurtosis is really high, it means the outliers are absolutely calling the shots in this distribution. Now, just as there was a different formula for when we've got a sample for the others, here is the sample formula for kurtosis. Obviously, you don't need to know this. This is insanely complicated, but Excel will do this at a click of a button. Key thing is that lurking in here is this fourth power here. That is what dominates. So outliers have enormous effects on kurtosis. So just as there is a skewness scale, there's also a kurtosis scale. Now, kurtosis ranges from 1 to infinity. And there's this key point at 3, and that's because the normal distribution has a kurtosis of 3. So if you see a distribution that has a kurtosis that's less than 3, it means that the outliers do less of the work in it. So for example, a uniform distribution, there aren't really any outliers there, so it's got much smaller kurtosis, whereas a distribution with a heavy skew is likely to have a much higher kurtosis. To confuse things more, most of the time people do not use the kurtosis scale as I presented it there. They use what's called excess kurtosis. Now, excess kurtosis measures kurtosis relative to the normal distribution. It's because the normal distribution is such an important distribution. When we measure things relative to that, it tells us basically what side of the spectrum it's on. So we center our scale at 0, and it goes therefore down to -2 and up to positive infinity. So excess kurtosis is just kurtosis minus 3. It's also what Excel gives us. So whenever Excel talks about kurtosis, it's giving us excess kurtosis. Let's have a look at an example. So here are two data sets, and I've constructed these specifically so that their mean average is exactly the same. Their standard deviations are almost the same, basically 30 each. Their skew is 0 for both of them because they're symmetrical. So what about their kurtosis? Well, the kurtosis for dataset A is 1.8 and it's 7.5 for B. And if we wanted an excess kurtosis, we just subtract 3 from these. Now, what does that tell us? It tells us that distribution B has fatter tails. And we can see that, right? Because dataset B is all bunched up. All of the data is 45 apart from these two. So these two outliers are doing loads and loads of the work. And what do I mean by loads and loads of the work? Well, they're basically responsible for all of the spread of the data. So those two outliers are responsible for all of that standard deviation, for example. A is just a uniform distribution because they're just spread out evenly, and so it has a much smaller kurtosis. In fact, it's got negative excess kurtosis, so it's less spread out than a normal distribution. So let's check that out in Excel. If you want the kurtosis, you just use the kurt function, and we select the data we want, and it's going to give us the excess kurtosis. So if you're interested in the actual kurtosis, you can just add 3 to that. But excess kurtosis tells you, since it's negative, it's got less kurtosis than a normal distribution. If we want it for B, I'll just drag that over, and there's the kurtosis for B, and there's the excess kurtosis for B. So very easy to do in Excel. So kurtosis is a concept that's often used as a measure of risk, and you'll sometimes see people in finance or kind of academic references to this talk about what percentage of kurtosis is accounted for by the biggest outlier or outliers. And so in this case here, if you look at A, 40% of the kurtosis is accounted for by the points which are the furthest away from the mean, whereas for B, 80% of the kurtosis is accounted for by the outliers which are furthest away from the mean. And what that tells you, if you were measuring risk, is that B is a kind of riskier proposition because when these outliers do happen, they have much more of an impact. Now, this is a little slide from Nassim Nicholas Taleb's book, The Statistical Consequences of Fat Tails, which shows basically a bunch of different securities and shows what percentage of kurtosis is accounted for by a single observation. So up at the top is silver, where the maximum observation, or rather the single biggest outlier, accounted for 94% of the kurtosis across 46 years, and hence that would be an example of a high risk security. So I just want to go through one example to show you what I mean by a single unlikely event having a big effect on the outcome. Suppose we were playing this game where a 100-sided dice with had one red face and all the rest were yellow. If you land on a yellow face, you roll a standard 6-sided dice and win whatever number it shows. Okay, so I roll this dice, and almost all the time I'll get a yellow side face up, and then I get to just roll a 6-sided dice, and if it's 5, I win $5, and if it's 1, I win $1, and if it's 6, I win $6, and so on. But if I'm unlucky and land on the red face, then I lose $350. And so what sort of data do you get when you play this game? Well, if I started generating data from this for a long time, I would keep on rolling. I'd expect to keep rolling yellow faces. And so the numbers that I would get from this distribution would be 5 or 3, and then 2, and then 2 again, and then 6, and then 5, and so on, and just normal numbers. And so for a long time, as I continued generating data with this game, I would have results which made me think that I was dealing, I mean, obviously if I didn't know what game I was actually playing, I would get results which would make me think that I had a very well-behaved distribution. And so if I started calculating the kurtosis of this data, it would be very small. And so it might be a long time, right? Maybe dozens, maybe hundreds of rolls. And then suddenly, after all of this well-behaved data, I get a negative 350. And then back to 1, and then back to 5, and so on. Now, if I generate enough data so that I can include that negative 350, I will get an enormous value for kurtosis, because a single outlier absolutely explodes the value of kurtosis. But it'll take me a lot of rolls to get there. And so why is this a caution? Well, sometimes when we have incomplete data, we can think we're dealing with a very simple, well-behaved distribution. We don't always know what the risks are that lurk in a distribution until we've spent a long time playing with it. I hope that's been a useful look at kurtosis. Once again, don't worry about the formulas. This is just about knowing how these things are used and a bit of intuition about where they come from. So that concludes our look at descriptive statistics of univariate data. That's data that just measures one thing. In the next video, we're going to take a quick look at correlation, which is a statistic for bivariate data. I'll see you there. So we've looked at lots of descriptive statistics for univariate data. We're now going to look at correlation, which is for bivariate data. This is where at each observation you measure two things. Let's have a look at how this works. So correlation is measured on a scale from -1 to 1, and it measures the strength and type of linear association. So what does that mean? Well, it means that if you have data that is arranged like this, where generally as the x value increases, the y value increases, that's relatively strong positive correlation. If you have data like this, where there's a bit of an association, a bit of a positive association, that's weak positive correlation. If you have data which is possibly randomly scattered, that's a correlation of 0. Correlation of maybe negative 0.2 or 0.3. Here's strong negative correlation, that might be close to negative 0.9. You can have perfect positive or perfect negative correlation. So it's just a number associated with the different shape of or layout of a scatter graph. Now it has a formula, which I'll show you. As always, this is not the important thing. You do not need to use this. I will not be testing whether you've learnt this at any point. This is merely to show you, and this is similar to the previous ones, that what we're doing here is we're on the numerator, which is basically going to control whether this is positive or negative and the size of it. We're multiplying the distance between each point and the mean in the x direction, and the distance between each y value and the y mean in that direction. And then we're multiplying them and then adding that up. So if you have any points which are big outliers in both the x and y directions, and then you multiply them together, that's going to have a really big contribution. So as always, outliers, not as always, but in many of the things we've looked at, outliers have a big effect on correlation. And we use the letter R to represent our correlation coefficient. So I'm just going to show you now in Excel how easy it is to calculate correlation. We're looking at our Bitcoin and Ethereum data again. The function we need is correl, short for correlation. You're just going to select this array, put a comma in, and then select this array. Close the brackets, hit equals, and this tells you the correlation. So the correlation between Bitcoin price and Ethereum price through 2021 was 0.53, so moderately strong positive correlation there. Okay, we're going to go straight into looking at some warnings now, how you need to be careful with correlation. And I'm going to show you this famous example. This is called Anscombe's quartet. Beautiful name for just 4 scatter graphs. Now the key thing about Anscombe's quartet is that when you look at these 4 data sets, they are clearly extremely different, right? We've got something which looks like standard positive correlation. We've got some kind of very clear relationship that's non-linear here. We've got a very strong linear relationship here with one big outlier. And here we have sort of no association, Y does not seem to depend on X apart from for this one point here. What's interesting about Anscombe's quartet is that on almost every metric that you could measure, they come out as the same. So the mean value for X in all four of them is 9. The mean value for Y in all four of them is 7.5. The variance, so S squared of X, is 11 in the X direction for both, and is 4.125 for both in the Y direction. They also all have a correlation coefficient of 0.82, and well, we'll look at regression later, but a line of best fit of 3 plus 0.5x. So on almost all of the measures that, well, all of the measures that we've, so on many of the measures that we've looked at in this course so far, these things come out as the same, but when you look at them, they're clearly not the same. So the moral of this story is that you can't only look at the descriptive statistics. Sometimes you need. So the moral of this story is that sometimes the things you calculate are not actually enough to give you a sense of what's going on. Often you need to graph and look at the data before you can understand it. Now, when we get this figure of 0.82 and think, oh, very strong correlation, that tempts us to think we could maybe predict Y from X. But the key thing here is that the only one that's actually going to work for is this one here. This one here has some very clear trend, but it's not a linear trend, and correlation measures a linear trend. So this is effectively meaningless here. It looks very much like this is a parabolic relationship, maybe the flight of an object through the air. This one here looks like this may have just been an error. I mean, it looks like we could predict results very well with a line that just runs through these points. And this one here, as far as we can tell, there's not really any association between Y and X. It's just one single outlier, which is dragging up this R value up something close to 1. Let's look at a few more cases where correlation is not appropriate. So in this data set here, I've got an R value of 0.88, which suggests very strong positive correlation. But you can see why that's come out, because in general, the data is clustered small x, small y, large X, large Y. But again, here, it's not really appropriate because, in fact, we've just got 2 patches, and really it looks like the data has been drawn from 2 different populations. In this one here, there seems to be no correlation really, and in this one here, no correlation, maybe a slight negative correlation. So any prediction you make based on this is likely not to be accurate, because within this population, there doesn't seem to be much correlation. Within this, it's certainly not strong positive. So one key thing for correlation, it has to all be drawn from one population. How about this example here? We get very strong positive correlation, but if I look here, it's clearly drawn from 2 populations again. And within each of those, there seems to be pretty strong negative correlation. So this is incredibly confusing here. So once again, look at your data. Right, it's good to work out these statistics, but until you've actually looked at it, you're not going to know really what's going on. So when can you use correlation? You can use correlation as a rule of thumb when your data is what's sometimes called approximately elliptical. So if you can draw crudely an ellipse, and if your data seems to sit neatly into that without enormous gaps in the middle, maybe getting thinner as you go to the edges, then it's a good contender for correlation. So if I worked out the correlation for this, that would be meaningful. But if it doesn't fit into some kind of ellipse nicely in a way that this doesn't, I mean, this one here, I could draw an ellipse, but there would just be an enormous gap in the middle of it. But if it can, then it's a good contender for correlation. Then you're going to have a meaningful result. So that concludes our look at descriptive statistics. These are the nuts and bolts we're going to be using for the rest of the course. And understanding these gives us So I hope you've enjoyed looking at descriptive statistics with me. That concludes So I hope you've enjoyed looking at some descriptive statistics. This concludes this part of the course. These things that we've covered in this chapter are the nuts and bolts of the rest of the course. So if at other points in the course you are hearing me refer to something like standard deviation or skew or median and need a refresher, just come back to this chapter as many times as you need, because we're going to be referring to these over and over again. So I look forward to seeing you in the next chapter. In this chapter, we're going to look at cleaning your data. We're going to talk about what that is and why it's so important for making sense of the data you have. So in this chapter, we're going to explore two main ideas. So first, in this video, we're going to look at anomalies and outliers, what they are, how to find them, and whether to remove them. And then in the next video, we're going to look at coding, scaling, and shifting, which can be a useful way of processing your data. So let's begin by looking at anomalies and outliers. So we're going to begin by looking at how to identify and remove anomalies. So these are data points which are either recorded in error or in some way don't fit with the sort of data you want to be collecting. After that, we're going to look at some formal definitions of outliers, how to discover them, and then whether or not to remove them. So let's look at anomalies first. So let's begin with this data set here, which is some data on various transactions made in a shop. So manager of the shop has the date and then every purchase and how much it was. And let's say we want to analyze this data with no specific goal in mind. We just want to get to understand the data. So we want to discover all the usual things. So average spend, maybe what the distribution looks like, whether it's skewed, this sort of thing. Now, if we're looking just for anomalies, what would that be in this case? Well, it's going to be any value which is not a number, right? We want just figures, in this case, amounts of money, or any amounts which are clearly an error of some kind. So one really straightforward way of doing that is just to filter your data and then order it from smallest to largest. Okay, so that's revealed something immediately. It's revealed that there are a whole bunch of spends which are zero. Now, if you are a data scientist, right, you would want to discover why zeros had been recorded. So maybe this is purchases that got cancelled or refunds, or maybe it was just people checking the price of something and it came out and the computer recorded that as zero money spent. Who knows? But this doesn't look like it's going to be useful data if I want to work out, for example, what the average amount of money was that people spent. So obviously, as a true data scientist, you'd probably confirm that with whoever you're working for, or you decide it for yourself if it's your business. But I'm just going to remove these now. Okay, let's say I discussed this with the manager of the shop, and they said, "Oh no, that's just how the computer records cases where." I don't know, where someone just asked what the price was or something like that. So I'm just going to delete all of those. And the other thing you might want to do is just flick through to the end, just in case there are any non-numerical values down at the end, anything non-numerical you'd want to remove. So right at the bottom, well, okay, so there's no non-numerical value. Okay, there is one enormous value, but we'll deal with that when we get to the outliers. But in terms of anomalies, everything else in this list, now that it's ordered, I can see is just a price. It's just an amount of money, and so that's fine. So that's all of the anomalies dealt with. I got rid of all of those zeros, which weren't really amounts spent in the shop. So now we'll move along and look at outliers. So firstly, just the intuitive definition of an outlier. So if your data is distributed like this, and let's say that we've got a mean value here, okay, and your data is, or let's say that's a median value or something like that, and your data is clustered around that mean or median, and here are these data points. Well, an outlier is any point which is far away from the average. Okay, so it could be over here, or it could be up here. And it's simply that. It's just a point which is a long way away from the average of your data. And why are we interested in outliers? Well, sometimes an outlier can be a signal that that data point was either recorded in error or was recorded in a different way, or for some other reason shouldn't be included in your data point. So it can be really useful to be able to identify outliers before you start doing all of the standard analyses of your data set. So I'm going to show you a couple of common definitions of outliers. So one of them relates to the mean and one of them relates to the median. So one standard definition of an outlier is any data point which is more than 2 standard deviations from the mean in either direction. So a little bit more technically, we might write it like this. Now, what does this mean? It means measure the gap from your data point to the mean. So that's x minus x bar. It's the absolute value of that. So it doesn't matter if you get a positive or negative result. It just measures the distance between your data point and the mean. And is that greater than 2 standard deviations? Okay, so that's one definition. Now, I've also put this here if you're working with population data, if you happen to know what the population mean was and the population standard deviation, it's the same thing. It's just the distance between your data point and the mean. And if that's greater than 2 standard deviations, i.e. if your data point is more than 2 standard deviations from the mean, then it's an outlier. So that's one definition, and that's useful if you happen to be working with means and standard deviations. An alternative definition, which is used if you're working with medians and quartiles, so maybe if you had very skewed data, you might use this, is more than 1.5 interquartile ranges beyond Q1 and Q3. So it's a bit of a mouthful, that. So now, as a formula, if x, your data point, is less than the lower quartile minus 1.5 interquartile ranges, or if your data point is more than the upper quartile plus 1.5 interquartile ranges. So let's explore both of these definitions with our shop data now. All right, so let's look at our first definition. So that was the one in terms of the mean, and it was if a data point was more than 2 standard deviations away from the mean. So the first thing I want to do is calculate the mean. So I just want the average spend. And that's £28.73. And I'll also want to know what the standard deviation is. So I want the sample standard deviation. That's generally the one we work with unless we know that we have all of the data of the full population. This is very much just a sample of data. Okay, so first thing to say is that the standard deviation is really high. Okay, and we'll look why in a moment. So at the top end, what we do is we take the average value and we add 2 times the standard deviation. So this gives us an upper bound. Okay, so that's the upper bound, which means anything beyond that point is an outlier. And for a lower bound, we want the mean, and we're going to subtract 2 times the standard deviation. Well, that's a negative value. So in this case, because it's money, there's not any negative values here, obviously. There are going to be no outliers on the lower end. On the upper end, we could look for those, or we could do a conditional format. That could be nice. So I could just select these cells and I could say highlight if they are greater than, and I can just put the value here. So the £100.68, and that's going to highlight those for me. So if I scroll down, I'm going to find that the outliers, there are some, they're down here. Okay, so these are the outliers using that definition. Now, whether I exclude these from my analysis depends on how they were gathered and what they mean. So I might discuss with the manager of the shop whether these were whether there was an error in recording these. Now, here's an absolutely enormous outlier. Now, suppose I spoke to the manager and it turned out that in fact this figure was from one regular customer who had requested to pay all of his bills for the last 10 shops all in one go, or something like that. And so really it didn't represent one spend, it represented 10 spends or 20 spends or something like that. You can imagine reasons why things might be recorded like this. So whether you exclude these depends really on what you're interested in. If you, when you speak to the relevant people, discover that they were all recorded sensibly and accurately, and they really do represent the things you're measuring, then that's fine. Then you can leave those in. Okay, so that is how we measure an outlier using the first definition. Now I'll show you how we calculate it using the second definition, which involved medians. So for this one, it was 1.5 interquartile ranges beyond either of the quartiles. So we need to work out the interquartile range. So we can do that, remember, using the quartile. We generally use the exclusive function. So if I take these numbers and I want the first quartile, so here's the first quartile, I'll put Q1 there. And for the second quartile, sorry, the third quartile, it's the upper quartile, I'll take the same data, but this time I want Q3. So there's Q3, and that means that the interquartile range is this value minus this value. Okay, so the alternative definition then is if a data point is your upper quartile plus 1.5 interquartile ranges. So that's our upper bound using this definition. And our lower bound is the lower quartile minus 1.5 interquartile ranges. And okay, well, just like it was before, it's negative, so there's going to be no outliers there. And again, we could identify outliers that way. In this definition, it's anything above £70.55, and that would give us, that would tell us which are the data points we would need to learn more about. So we don't automatically reject outliers; we just inquire how that data was gathered, what they represent, and whether they need to be excluded from the data. Let's now try to apply these definitions in the following case, which is data about the inflation rate in the USA between 2010 and 2021. So pause the video and have a go at this yourself if you can. So remember our first definition was the gap, if the gap between our data point and the mean is more than 2 standard deviations. Now, in practice, it's often easiest, as I showed you on Excel, to just find an upper and lower bound. So the way we do that is we take the mean and we add or subtract 2 standard deviations. So that's a kind of way of finding the upper and lower bounds. So let's go and do that in this case. Let's find the upper and lower bounds using the mean plus 2 standard deviations and the mean minus 2 standard deviations. Okay, so we can calculate the mean just using the average function. We can calculate the standard deviation. We'll go for the sample as always, as usual. And so our upper bound here is going to be the mean plus 2 standard deviations, and our lower bound is going to be the mean minus 2 times the standard deviation. And so this gives me my upper and lower bound. So the upper bound is 4.24 and my lower bound is minus 0.3. So now that we've got these upper and lower bounds, so my upper bound being 4.24% and my lower bound being minus 0.3, I now just check to see if any of these fall on the wrong side of these. Well, there are no negative values, so there are no outliers on the lower bound, but there is this 4.7 here at the end. So that one there is an outlier. Now, do we exclude that? Well, I don't think so in this case because it wasn't recorded in error. It's not going to completely destroy all of our analysis that we'll want to do about this. In this case, we'll probably leave it in, unless we wanted to know something like how does the inflation rate vary in typical years. Maybe 2021 was not a typical year when it came to inflation, and maybe what we want to know about is inflation in what an economist might call a typical year. So that could be one reason, but it doesn't seem to be particularly strong reasons for rejecting this one now, but it is an outlier. Okay, looking at our other definition, which is the upper bound being the Q3 plus 1.5 interquartile ranges, or Q1 minus 1.5 interquartile ranges. So let's try to apply both of these. Remember that in practice, you'd probably just use one because you'd probably be either using your means and your standard deviations or your medians and your quartiles in your analysis to begin with. I'm just showing you how both work. So let's work out the upper and lower bounds using this definition now. Okay, so for this, I need the upper and lower quartile. So the upper quartile, so quartile X, the exclusive one, and we'll go for the quartile 3. And then the lower quartile, so we want this data, and quartile 1, which means my interquartile range then, so my interquartile range is the upper quartile minus the lower quartile. So what does this mean? It means my upper bound, the point beyond which we'll call something an outlier, is the upper quartile plus 1.5 interquartile ranges, and my lower bound is the lower quartile minus 1.5 interquartile ranges. Okay, so those are my bounds, 3.94% and minus 0.27. So with this definition, we had an upper bound of 3.94 and a lower bound of minus 0.27. So once again, we have no outliers on the lower bound. Beyond the lower bound, we do have the same outlier on the upper bound. So both definitions picked out the same year as being an outlier in the data. So I hope that's been a useful look on how to find outliers. Remember, the key thing is once you've found your outliers, you then need to investigate more about those outliers. Were they recorded in error? Do they mean something different? Are they really what you want to learn about? And remove them from your data if necessary. But these two methods that I've shown you are the two most common methods for identifying outliers. Having looked at how to identify and remove anomalies and how to find and think about outliers, we're now going to look at coding data, which is scaling and shifting your data. So we're going to look at when this is done and how to handle it. So I'll admit coding is a slightly confusing word for this topic. It's got nothing to do with computer coding like Python or Java, nothing like that. It's about repackaging your data or translating it into some other form. Let me give you an example. So as we all know, temperature is recorded in two common ways, Celsius and Fahrenheit. And depending on which side of the Atlantic you might live on, you're used to one more than the other. So suppose we had a bunch of temperatures that had been recorded in Fahrenheit. And we calculated some averages and standard deviations. We got an average temperature of 64 degrees Fahrenheit and a standard deviation of 15 degrees Fahrenheit. But suppose what we actually wanted was to report these results in Celsius. Well, the formula of converting Fahrenheit into Celsius is this. You take the temperature in Fahrenheit, T, you subtract 32 and then you multiply by 5/9. Slightly bonkers formula, but that's what it is. So with that known, that coding formula, could we figure out what the average temperature is in Celsius and what the standard deviation is in Celsius without converting all of our data? Right, we could just use this formula to convert all of these data points into Celsius and then calculate means and standard deviations. But obviously that could be very time consuming, and maybe your data set has 1 billion data points, in which case it would be far too time consuming to do all of these conversions. So we want to be able to just take that formula and use that to convert these. So how do we do that? Well, let's think through some examples. We're going to think about shifting and scaling. So let's think about scaling first. So by scaling, I mean taking some data points and doubling them. So one very simple coding formula would be y equals 2x. So whatever your previous data point was, double it. So what does that look like? Well, here are 3 data points and their mean calculated. Now, if I double all of these, here's what happens. So I've doubled all of the data points, and what we can see is that they've obviously all shifted along. Now let's think about what's happened to the mean and the standard deviation. So clearly, well, I think clearly, hopefully you think clearly, if you double all of your data points, the mean will double as well. Okay, clearly if all of the data points are now bigger, the mean average will also be bigger, and we can see that here. What about the standard deviation? Standard deviation is a measure of spread. So let's think about what happened to the gaps between our terms. So this gap became this gap, it doubled, and the gap between these 2 points became the gap between these 2 points, it doubled. All of our gaps doubled. What that suggests is that the spread of data doubled as well, and that is in fact the case. So when you have a coding formula which is a scale factor, that will apply to the mean and the standard deviation. And the reason is when you double data, it doubles the mean. Okay, clearly making all the data bigger makes the mean bigger, but it also makes the gaps between the data bigger as well. So that's scaling. What about shifting? So let's look at this, another very simple formula, y equals x plus 2. So our previous data, our yellow data, we're just going to add 3 to it. And what does that look like? It looks like this. Okay, we've simply shifted those points up by a factor of 3. So what do you think that did to the mean and standard deviation? Well, for the mean, once again, hopefully it's obvious. If you bump all of your data points up by 3 units, the mean will get bumped up by 3 units as well. What about the standard deviation? Well, what happened to those gaps? The gap between these 2 points became the gap between these 2 points. Well, what's that done? Nothing. It hasn't changed the gaps at all. So that's really important because it means that shifting, so anything you add or even subtract to data, has no effect on the standard deviation. Okay, so let's put that all together in the following way. If I had a coding formula which took some previous data, x, multiplied it by a, so that's my scaling, and added b, so that's my shifting, what happens to the mean and the standard deviation? Well, here's what happens. The mean of y is simply the mean of x put into that formula. So you multiply it by the scale factor and you add the constants, that does the shifting. So really straightforward. With the mean, multiplying and addition or subtraction both affect it in the way that you'd expect. What about the standard deviation? Well, we saw that shifting data has no effect on the standard deviation, but that scaling does. And so what that means is that the standard deviation of your new data set is simply the standard deviation of your previous data set multiplied by the scale factor, and b did not come into it at all because adding stuff to your data had no effect on the standard deviation. So since this is the formula for standard deviation, if you were interested in the variance, which is just the standard deviation squared, it would be this. The variance of y, so the square of the standard deviation here, is a squared multiplied by the variance of x. So that's the relationship between their variances. So there we have it. If you have data which you've coded up, the scaling affects the mean and the standard deviation, but the shifting only affects the mean. Okay, so we can use that fact now to solve this question. So if we have this formula, which relates Celsius and Fahrenheit, if we want to find the mean in Celsius, we just put the mean for Fahrenheit into this formula because both the scaling, the 5/9, and the shifting, the -32, affect the mean. So all we're doing is putting our average temperature in Fahrenheit, which was 64, into this formula here. And when you do that, you get 17.8. So 17.8 degrees Celsius, that is the average temperature in Celsius. What about the standard deviation, S, I'll put S sub C, so the standard deviation in Celsius? Well, for that, we ignore any shifting. Shifting has no effect on it. So we ignore this -32 here, and it's simply 5/9 of whatever the standard deviation was before, which was 15. So 5/9 of 15, and that is 8.3 degrees Celsius. So that's how we use these coding formulas when you have coded data. Here's another example. A scientist collects data on the mass, so m grams, of samples of metal. He codes the data using the formula x equals m minus 1200 divided by 10. Now, why would you do that? I mean, that's a valid question. So it might be that almost all of the samples were very, very close to 1200, for instance. And so moving them all relative to 1200, maybe 1200 is a long-term average. So subtracting 1200 tells the scientist whether these samples are above or below the average, for example. And dividing by 10, again, it might just be that a lot of them are big, and so dividing by 10 just means it's smaller numbers to work with. Okay, so given that the average of x is 2.1 and the standard deviation of x is 1.4, calculate the mean and standard deviation of the mass of samples. So this would sort of be working backwards here. Okay, so how do we do that? Well, for the mean, we know that the means are related and they factor in the scaling and the shifting. So the mean of x, which we know, it's 2.1, is equal to the mean of m minus 1200 over 10. And so we're just going to solve this equation here. So multiplying through by 10, we get 21 is equal to the mean of m minus 1200. And that means that the mean of m is equal to 1221. And then for the standard deviation, well, they're related in such a way that the scaling is relevant, but the shifting is not. So what that means is that the standard deviation of x, 1.4, is equal to the standard deviation of m, but we ignore the minus 1200 because that's just a shift, and we ignore that when we're comparing standard deviations, divided by 10. And so all I need to do is multiply both sides by 10, and I get the standard deviation of m is equal to 14. So that's another example where the coding formula is set up a bit differently, but the logic is still the same. The scaling is factored into means and standard deviations, but the shifting is only factored in to means. Hope that's been a useful look at coding your data, shifting and scaling. Look forward to seeing you in the next video. In this chapter, we're going to look at visualizing data. So once you've crunched some numbers, once you've gathered some data, very often what you need to do is present your findings to other people. And the different ways we have of visualizing data can help your audience understand what you've discovered about your data. So in this chapter, we're going to look at a wide range of different techniques for doing this, look at the pros and cons of these different techniques, and look at how we do these in programs like Excel. So we're going to begin by looking at line graphs, one of the most common forms of displaying data, often associated with changes over time. Then we're going to look at bar charts, similar kind of idea. Next, we're going to look at dual axis charts. This is a way of displaying two types of information on one graph. Then we're going to look at pie charts. We're going to look at the more complex ways of displaying data. So we're going to start with histograms and box plots and cumulative frequency curves. And finally, we're going to bring it all together and look at comparing the different sorts of visualizations and think about the pros and cons of each one. We're going to begin, though, by looking at line graphs. So let's begin by thinking about how we would visualize some data like this. So what I've got is the data month by month of the number of signups to a particular website. Well, one very natural way to do this is using a line graph like the following. So what is this showing us? Well, it's basically just plotting the number of signups on the y-axis and the month on the x-axis. And what this allows us to do is see that there is, we can see what trends there are if there are any. So in this case, there is overall a general trend upwards, but it's quite variable and there are some significant ups and downs. So let me show you how to generate this line graph in Excel. So this one's a really simple one. Here's our data. All we need to do is select all of the data we want and insert, and then it's this one that we want here. So line or area chart, and just the sort of standard line graph here is pretty good. So there we've got it. Now, one difference you might notice between this and what I had up before is that my axis here, I didn't have starting at 0. Now, you need to be a little bit careful, or at least honest about this. Sometimes small changes, and these are relatively small changes, are easier to see if we don't have our y-axis going all the way starting at 0. So let me show you how to do that. But it's important, I think, when you display this data, when you talk about it, to acknowledge that, to draw that to your audience's attention. Because when I change the minimum value on the y-axis here, okay, it looks like this now. So the changes are easier to see because they're magnified. But the reason I bring up the idea of honesty here is that you might think that the number of signups looks like it's sort of more than halved between here and here. But actually it hasn't. It's gone from 68 to 56, which hasn't halved. It's just I'm starting my axis at 50. So changing the y-axis is fine and can make changes easier to see, but it's obviously worth being clear to your audience that you've done that, or just highlighting that if you're ever talking about it. So that's how you create a line graph, and that's how you change the axis if you need to make things clearer. So these sorts of line graphs are often called time series graphs. Now, the reason they're called that is that very often, but not always, the x-axis values are time values. So here I've got a graph of sea level change, and we've got time here. And so it's a sea level change since 1870. And so this is a good use of a line graph here. It's clear to see what the trend is. And yeah, this is why we often call it time series, because very often, but not always, the x-axis values are time. Let's have a look at some good uses, or some interesting uses. So sometimes we can have multiple different sets of data all on the same graph. So here's a graph which shows labour force participation rate. It's seasonally adjusted, and it's just for men between 25 and 54, so quite a specific data set. And it's going back down to 1980 and all the way up to recent years. And this is good because we picked out a few countries. We can see that there is a downward trend in all countries, but we're able to see how particular countries have fared. So in this one, the United States one has been made bold. So whoever made this graph is highlighting a particular fact about the United States there. But having multiple line graphs and multiple time series graphs on one chart can be really useful for highlighting how different data sets change and move together. Let me show you how to create one of these. So here I've got my sign up information again, but now I've got two sets of data. Let's suppose this is two competing websites. So here's the data we were looking at before, and here's a competing website. And so here's a graph which shows the sign-ups for each of them. And the reason why this is really useful is it can show not only the individual trends that relate to each of your data sets, but also how they compare to each other. So what we can see is that there is a general increase in both, but the gap between the two is tightening. And so that could be of interest. Let me show you how to create this graph. So when you have your multiple data sets, you just select all of the data as well as the months here. They're going to automatically become the x-axis. Select our line graph and it knows what you want to do. Now, similarly, I'll just get rid of chart title. You can rename that if you want. Now, similarly to before, since all of the data sits kind of between 50 and 90 or so, I'm just going to change this axis here so that the differences and changes are a bit clearer. So I just change that to 50, but you don't need to do that. It's just important to be clear about it to your audience when you are. So there we go. So I think that looks a little bit clearer now. So that's how you do it on Excel. You just select your data and click line graph. So as I said, often the x-axis values are time, but not always. So here's an example of a line graph that uses that has temperature on the x-axis and density on the y-axis. This is showing the relationship between temperature and density of water. And this is a line graph as well. It's just not a time series graph. So this shows that if you increase the temperature of water, its density falls, and then you can see the trend. Here's quite a nice example of a line graph which is not a time series graph technically. So what this shows has a bunch of tennis players, and on the x-axis is not time overall, it's the age of each of these tennis players, and on the y-axis it shows how many Grand Slam titles they won. So this is nice because despite all of these tennis players playing at different times in history, we're able to make comparisons of how rapidly they won Grand Slams. So you can see, this one is very steep. So Steffi Graf won her 22 Grand Slams quite quickly, and then there's got a less steep one. So Serena Williams, who won one more Grand Slam, but the line is slightly less steep. So you can see it took her a little longer to achieve that. So this is quite a nice creative use where rather than time on the x-axis, it's the age of the different tennis players. Okay, let's just think about when to avoid line graphs. So generally when we use a line graph, it's because the thing that we're measuring on the x-axis is either time, which is obviously ordered, or some other quantity which can be ordered. For example, age, right? We can order the ages of the tennis players, or temperature, where we can order the different temperatures. We really do need to be careful. I think we just avoid actually a line graph where the categories down here are not ordered. Otherwise, it can be incredibly confusing. So this is showing the number of players of different games in a casino on Wednesdays compared with Sundays. Now, when we look at this, it is meaningful, like it makes sense. I can see that generally there are fewer Sunday players on almost every game, apart from blackjack maybe, than on Wednesday. And it also, I can see what the most popular games are. So I can see that spades is the most popular game, and there's a kind of ranking of popularity. But the reason why this is very confusing is that your audience will interpret this as some kind of trend. There's something that we're measuring is increasing. And although what's increasing is the popularity, there's no inherent ordering of these concepts here. Right? There's nothing intrinsic to these games which has them ordered in this way. So when I see a sort of trend number of players, your audience will always interpret that as something is increasing. And that's not actually what's being displayed here. Nothing is increasing. We just have varying rates of popularity by games. And so there will be other methods of displaying this kind of data other than line graphs, which will do a much better job. And we'll look at that kind of thing later on in this chapter. So avoid line graphs if your x-axis categories are things which don't have any sort of intrinsic ordering to them. Okay, that's all on line graphs. In the next video, we're looking at bar charts. In this video, we're going to look at bar charts, quite a closely related concept to line graphs. Once again, we'll look at how to do it, when to avoid it. So in the last video, we looked at this line graph that was showing how the number of sign-ups varied across a year, monthly sign-ups. So a bar chart is very similar really to a line graph. Instead of joining all of the dots with a line, we just draw a bar up to each of our points, lose the line, and that is a bar chart. So fundamentally, it's very, very similar. There are a few differences between how we use line graphs and how we use bar charts, and that's what we'll explore in this video. The first thing we'll look at is how to draw a bar chart that shows multiple data sets on it. So we saw in the last video that we can have a line graph that shows 2 or more sets of data. I'll show you how to do that for bar charts as well. So if we have our data here on signups for 2 websites, very similar, we just select the whole thing, and now we're selecting the bar chart option. It's just the first one. You can use the 3D ones if you like the look of those. I'm just going to use the 2D ones. And here's a bar chart that shows the relative signups, well, not relative, it shows the signups of website X and website Y. And if we want, we can change the Y-axis, but this is less advisable when we're dealing with bar charts. So it can become very misleading when you do that. So that's how you do it. In this case, I'd probably favor the line graph because the line graph, I think it's easier to see the trends in this case, but it's not an unreasonable example of when you might use a bar chart as well. So unlike line graphs, with bar charts, it is sometimes acceptable to have your categories on the x-axis to be things which don't have an inherent ordering to them. So you still need to be careful, but I think this is an example of where the graph does actually show clearly what it intends to. So this is a measure of frequent use of media by supporters of different presidential candidates back in 2015 or something. So what this shows along the x-axis is different categories, different ways for people to be getting their news. And obviously there's no real ordering of these, but actually the eye is not drawn to overall trends here. It's drawn to differences within each category. So what I can see here is that the Clinton and Sanders supporters are more likely to be getting their news from national media, whereas the Cruz and Trump supporters less so. And so it's these comparisons which I can clearly see. Over here, late night comedy, it's less likely for both, but it's present for Clinton and Sanders supporters and almost non-existent for Cruz and Trump supporters. Or cable TV, I can see a spike here for Trump supporters. So I'm able to make some comparisons, or this one where 3 candidates is basically all the same for internet, but Sanders, there's a big spike there. So this one's okay because not showing trends across over time or anything. I'm not interested in what the trend is as I move from left to right. I can just look at each category and see what I can learn in each one. So newspapers, I can see that Clinton supporters go to newspapers most, followed by Sanders, followed by Cruz, followed by Trump. So it's meaningful and presents quite a lot of data, even though the x-axis is not an inherently ordered data set. So unlike line graphs, it can be okay for bar graphs. Another thing we can do is have stacked bar charts. So stacked bar chart, something like this. This is showing shark attacks between 2005 and 2014, and the light blue shows non-fatal attacks and the dark blue shows fatal attacks. And the reason why this is good is that the overall height shows me just how many shark attacks there were, and then the ratio of light blue to dark blue shows me the relative frequency of non-fatal to fatal attacks. So it tells me 2 bits of information in one go: how many shark attacks there were overall and what fraction of them were fatal. So for instance, what I can see from this graph is that between 2011 and 2012, shark attacks did go up, but the number of fatal shark attacks went down. So it shows me multiple things in one go. Let's look at how we could create a stacked bar graph for the following. So suppose that a company is paying for advertising and it's kept track of how much it has spent on advertising from different media outlets. So across a year, it spent this much on Facebook advertising in month 1, and then this is how much it spent across the year, and then Google, and then newspapers and TV. So let's look at how we would create a stacked bar graph for this. So to create this stacked bar graph, we just need to select our data. And when we go to insert a graph, we go to bar graph here, and then it's this one here. So this is a stacked column bar graph. And the reason why this is really nice is that just like with the shark attacks, it shows both the total amounts, in this case that's total advertising spend, because I can keep track of that and see that, okay, although it went down a little bit, it was relatively stable across the year, but it also shows the ratios within. So I can see that the ratio spent on Facebook has gone down, whereas the amount spent on Google has increased, the amount spent on newspapers has gone down, and then the amount spent on TV has varied a bit, but generally stayed stable. So it shows quite a lot of information all in one go, so it can be a really good option. So finally, we'll look at bad uses of bar charts. And The thing you need to be most careful of with a bar chart is meddling around too much with the y-axis. Now, I've not only said that's okay, but I've even encouraged you to do it when you're dealing with line graphs. With bar graphs, it can be really misleading, particularly when we're dealing with multiple data sets. Have a look at this. So this is showing news magazine staff size over time. So it's comparing Time magazine and Newsweek magazine and how many people they employ. And if you don't pay too much attention to the axes, what this seems to be showing is that Newsweek staff has dropped to an absolute fraction of Time. They've both gone down, but Time magazine, well, theirs just dropped by a little bit every year or across time, whereas Newsweek's absolutely plummeted. And it looks like Newsweek now employs, I mean, who knows, about, what is that, an eighth or something of Time. But that's not true, and it's not true for the following reason. This y-axis here doesn't start at 0. So what's happened to the staff of Newsweek? Well, it's dropped from, well, they were both around 350 or 360 there, and they both dropped, but Time has dropped to about 300, and Newsweek has dropped to about 180. So 180 to 300, I mean, Newsweek still have more than half as many staff as Time, right? Time do not have twice as many as Newsweek, and it looks like it does here. The other thing to be careful of is if you do have your time, whatever units it is, across the x-axis, it's much clearer if they are proportionally spaced, and that's not what we have here. We have 1983, 1993, 2003, 2004, 2005. So the comparison of 83, 93 and 03 is fine because they're just 10 years spaced apart. But then these two here are 1 year spaced apart. So it's a very confusing graph because it makes me think that Time magazine just had a sort of steady rate of decline. But that's not true because the steady rate over that decade and that decade, although it looks like it continued here, these were 1 year gaps rather than 10-year gaps. That's a much steeper decline. And the changes in Newsweek, well, that looks like a kind of steady decline. And then over here, it looks like there's a kind of very slow increase. But actually, these are across 1 year intervals. So the tiny little increases there are actually quite significant because they're happening over 1 year and not over 10 years. So all in all, this is an example of a very confusing bar chart. If you're creating a bar chart, using a bar chart, make the x-axis units evenly spaced if they are things which have an order like time. And if you're comparing multiple data sets, it really is a good idea to set your y-axis down to 0. Otherwise, it can really mislead the comparison, look like that one data set is a fraction, the other is much smaller than it really is. I hope there's been a useful look at bar charts and you now feel confident using them to present your findings. Let's now look at dual axis charts. These are methods for showing different data sets, measuring two different things on the same graph. So let's take a look at a dual axis chart. Here's an example of one. Let's see what it's showing us. So the blue bars, they're showing recent homes sold. So the number of homes sold. And that over here is measured on this axis here. So what I can see is across these months, the number of homes sold in whatever region is being measured here was, around 280 and then dropped to about 150 and then increased and so on. But we have a separate data set with its own separate axis being measured with the orange line graph. And that's the average price of homes. And so the axis over here on the right-hand side, well, that's showing the average price per home. I assume that's in thousands there. And what we can see is that that starts off at 400 or so, and then it increases to around 450, and then it declines. Now, this is a useful way of presenting data because it can show how two different data sets relate to each other. Now, what we can see is that when the number of homes sold was at its lowest, that was when the price was at its highest. Okay, and then as the price went down, well, the story with number of homes sold is a bit complicated, but at least we can start to understand what's going on and possibly draw conclusions. Notice as well that the y-axis here for the average price doesn't even begin at 0, whereas this one does. And that's okay, as long as we're not trying to deliberately obscure the information, as long as we're clear about it. So this is called a dual axis chart. Let's have a look at how we create one. So suppose that we wanted to show a dual axis chart for within a company, let's say how many employees it had across a number of years and how much profit that company was making. So let's go and do this in Excel now. Okay, so here's the data. Let's have a look at creating a dual axis chart. So there's quite a lot to actually do here. I'll try to explain it in each case. So first thing to do is select your data. And initially you can just select any old graph really, but let's just do a line graph. So this is not at all what we want. Let me just explain what Excel has done. It has first looked at these numbers here and given us a line graph of those. So that's 2010, 2011, etc., which is not at all what we want. We don't want to graph these. We want these numbers to be the x-axis. It's also then just created a line graph of these numbers in orange and these numbers here in grey. So first thing to do is get rid of this line here. So here's how we do it. We click on our graph, just make sure it's selected, and we say select data. Now, in here, these three things are the three things that the graph is plotting. Now, we do want employees and we do want profit, but we don't want year. So click on year and remove. That's now taken that out of the graph. When I click OK, well, no, it's already done it now. Now, the other thing is I don't want 1, 2, 3, 4. It's just done that as a default. Like here's the first entry, here's the second, here's the third. I want these years to be my x-axis. So I can edit my horizontal axis and I can select the terms or the years in this case that I want there and they just appear. Okay, and there we have it. So that's the first thing cleared up. Okay, but this is still not a dual axis chart. This is just a double line graph. So to turn this into a dual axis chart, click on your graph. I need to click on chart design here. And we want to change chart type. Now what we want to change it to is a combo graph. So this has given me a suggestion here that one of these things is going to be a line and one is going to be a bar chart. So I'm happy with that. Thing is, it's not dual axis even yet because I don't have a secondary axis here. Now, it's really up to me which one I have as my primary axis and which one I have as my secondary axis. I think since we've got employees on the left-hand side here, I'm going to keep employees as my primary axis and I'm going to put profit as my secondary axis. So let's have a look at what we've got now. So what's this showing? I'll just get rid of this chart title. Well, this is showing employees as the orange bars, ranging from 6 employees here up to this bar with 65 employees. And the grey line here, I'm looking at this axis over here. This is showing profit, which started down here at 125 and went up till around 400 over here. Now, the final thing I might want to do, in fact, I definitely should do, is label these axes. So how do I do that? Well, I want to add a chart element. And it's axis titles I want. So let's give my primary vertical axis a name. So over here, this was employees. And I'll also add a axis title for my secondary vertical over here. And this one here was profit. And that was in thousands of dollars. And so there's a nice looking dual axis chart. Now, just with any chart, you can fiddle around with the y-axes here, either one. If we wanted, for example, profit not to run from 0 to 400, but wanted to run from, I don't know, 100 to 450, That's okay too. I'd say in this case, that probably just um, adds confusion for the sake of it. So I probably wouldn't do that in this case. But if your data is very hard to visualize without doing that, then that's okay. So that's how we do it. That's how we create a dual axis chart. It can be a very useful way of clearly showing the trends of two data sets, particularly if they're both measured across time. We're now going to look at pie charts, a useful way of showing relative frequencies of different things measured. So suppose we had some data on proportion of the vote secured by 5 different parties. And let's think about how we could clearly display these results. We're going to start by thinking why the previous methods we've looked at don't work so well. So one thing we could do is draw a line graph, but this is very confusing because, well, for one thing, it kind of violates this idea that with the line graph, the the categories you have on the x-axis should be ones that have a natural ordering to them. And party A, B, C, D, and E, apart from the fact that I've given them names which are alphabetical, there's no natural ordering for those parties. So that's no good. It makes it look like something is decreasing over time, which is obviously just not true in this case. What about bar graphs? Well, that suffers from the same thing. We also want to avoid categories that don't have an order unless we're making comparisons within each group. And so this isn't a particularly useful way of displaying it. However, this is where the humble pie chart shows us really nicely what's going on. I can clearly see here that party A secured a really nice big chunk of the vote, and it gives me a sense of how much bigger it was than other parties. I can see visually how much bigger party A's share of the vote was than party E. I can also easily spot trends like the fact that party B, C, and D combined got more than half of the vote. So little details like that often pop out from a pie chart. And then what is a pie chart doing? Well, it's just taking 360 degrees of a circle and assigning these percentages of that. So we're taking 40% of 360 degrees, and that's the angle that this section gets. We're taking 23% of 360 degrees, and that's what we're getting here. Now, obviously, there is a calculation that you can do to work that out. So, if you want to know precisely what angle it is, well, we're just taking 40%, so 40% of 360 degrees, and we work out what that is, and that's going to be 144 degrees. So, there is a calculation that you can do in each case, but in reality, we're not doing this with pen and paper. We're going to do this with something like Excel. So let me show you how to do that. Okay, so with our data here, it's pretty easy. We're just going to select the whole lot, and when we go to insert a graph, it's pie chart here. And just a standard 2D pie chart will be fine for us. So this really kind of sorts it all out very nicely. If you don't like the colors, you can go and edit those if that's your fancy. You can go in here and fiddle around with what colors you want for your charts. But otherwise, it generally does a good job of presenting all of your data nicely here. So that's what a pie chart is. And as you can see, it does a pretty good job at highlighting when different proportions are of interest. And it does so particularly well if there are a relatively few number of categories to compare. So let's have a look at a situation where a pie chart would not be so useful. So over here, being a big football fan, I've got in some sense, the list of the best strikers of the 20th century according to goals per game. So what we have is Lionel Messi at the top with 0.87 goals per game across his career, and it is the top 20. So we could organize this in a pie chart, and it would look like this. But this is really a disaster because it's extremely difficult to see. I mean, if you really pay attention, you can see that the sector here for Messi is bigger than the others, but it's not clear by how much. And certainly almost all of these look almost completely the same. It just gives no sense of how much better this player was than everyone else. So when you've got too many categories, pie charts are really not a good idea. Um, Apart from that, they do a pretty good job. If you just have one thing being measured and a small number of categories, and what we're interested in is not the absolute values, but just how they compare, it does do a good job, but not if there are loads of categories. So let's think about how we would display this data. So here's a bar graph. I don't think this does a very good job either. For one thing, the x-axis down here, well, certainly these players, there is nothing inherent about those players that lends them to an ordering. I mean, I've imposed an ordering on them, which is why you see this downward trend. But there's nothing about the players which says we should order them like this. Okay, so in trying to figure out which method I should use, I suppose it really depends on what it is I'm trying to highlight. So what I could do is I could just take the average of all other players and compare that to Messi, and that's okay, but it's quite boring and really doesn't give that much of a sense of what an amazing accomplishment this was. So one really nice creative example of a way that I think is a great way to present this data is the following chart. So this is a bit like the one we saw with tennis players before, where, I mean, this is actually measuring just goals rather than goals per game. But what we've got on the x-axis is age, and we've got on the y-axis is goals. And what's cool, this is from a website where you can actually select well, any of these players. We've got hundreds of players here, then a few key ones picked out. And what's so great about this is you can see by the steepness of the graph how much better Messi and Ronaldo were across their careers than everyone else. Because you generally players score, and this is just top strikers anyway, are kind of scoring at a rate which sees their lines increasing at sort of that gradient, whereas these two players, it was just much steeper. And it's also nice because for younger players, you can see how they're doing compared with these two great older players. So this is a nice creative way of making that comparison where highlighted the players you want to focus on. In the background, you can see what the kind of trend of lots of other players was. So just showing you that there are often creative ways to display your data apart from the kind of standard ones that we've looked at. But yeah, pie chart definitely avoided when you have too many categories to focus on. We're now going to look at an altogether different type of visualization, and that is the histogram. So I'm going to show you what a histogram is, how to create one. So histograms are for showing you the distribution of your data. They're specifically for continuous data forms, so that's data that could take any value, things like height, where within a particular range, your height can be anything. It's not confined to whole numbers, for example, or weight, or things like this. And when you've gathered lots of data and you want to see how that data is distributed, histograms are brilliant. And key to histograms is that what you are graphing is frequency modeled as area. So when we looked at bar graphs, we had frequency represented as the height of the bar chart. With histograms, it's area. So let's have a look at the following example. So what I've got here is some data about the weight of a random sample of 60 carrots of a particular variety. So I'm starting off with something particularly fascinating here. So we've got weights of carrots across a number of different brackets here. So the reason why we don't just plot frequency as height is that that would make things really confusing. So consider these two numbers, 10 and 11. They're pretty similar. If you just plotted these two as the heights, it would make you think that the kind of 30 to 50 range is as common as a 50 to 60 range, which, well, that point, as I stated it, is technically true, but 50 to 60 is a 10-gram range. This is carrots weighing between 50 and 60. Here we've got a 20-gram range, ranging from 30 to 50. So we had a similar number of carrots, but across a much wider range, which tells me that carrots in general cluster more in this range here. Even more so here, we've got 18 in this 10-gram range. In fact, all of the rest of them are 10-gram ranges as well. We've just got an extra wide section here because there were not so many carrots there. So by representing frequency as area, it gives a really clear sense of what the underlying distribution is. I'll talk more about the underlying distribution in a moment. So let's look at how we do this. So if we want frequency to be proportional to area, what we're going to do is we're going to represent each of these categories as a rectangle, as a box. And on the base of that box is going to be the class width. So that's the 30 to 50 here. And the area is going to represent the frequency. So the formula that we're going to use for this is that we want frequency to equal the base of the rectangle. So that is the class width multiplied by the height. And we're just going to create a new term for this called the frequency density. So that's what FD stands for here, frequency density. And we can work out these frequency densities by just rearranging this by dividing through by class width. So our frequency density is going to be our frequency divided by our class width. So we basically created a new statistical concept, frequency density, specifically so that it ensures that the area of our rectangle, our base times our height, is equal to the frequency. So let's see what that would be in each case. So my frequency density here, well, it's my frequency divided by my class width. So that's 11 divided by 20. So 11 divided by 20 is 0.55. And in this case, my frequency divided by my width, well, frequency is 10 and my class width is 10. So that's a frequency density of 1. Over here, I've got a frequency of 18 and I divide it by class width of 10. The reason why it's class width of 10 is it takes us from 60 to 70. So that's 1.8. Here we've got frequency of 14 divided by class width of 10, so 1.4. And finally, we've got a frequency of 7 divided by class width of 10, and that's 0.7. Okay, so I've just put some values up here for my y-axis. And the reason why I've picked these is that I need frequency densities that range from, well, somewhere close to 0 up to somewhere close to 2. So let's show you how we create these boxes then. This first one is going from 30 to 50, and it should have a height of 0.55. So it's going from 30 to 50, and it should have a height of 0.55. So here's 0.5, and 0.5 is about there. Now, obviously, in reality, you're not doing this with pen and paper so much, but it's good to see it done once. So there is my box that represents the 30 to 50 group of carets. And the key thing now is that this box has an area of 11 because it's got a height of 0.55 and a width of 20, and 20 times 0.55 is 11. That's how we constructed that number of 55. So this one represents 11 carets. Okay, our next one goes from 50 to 60 and should have a height of 1. So from 50 to 60, and it should go up to 1 here. It's supposed to be a straight line, it's supposed to be one straight line. And that's my second histogram, that represents 10. And now you can kind of see why area as frequency is pretty good. Because these two boxes clearly have a very similar area, that intuitively tells us correctly that that represents similar numbers of carets. Just these ones are more bunched together in the 50 to 60 range rather than the 30 to 50 range. The next one goes from 60 to 70 and should have a height of 1.8. So it should go all the way up to 1.8. So that's about here. Again, we're doing this either with a ruler carefully in our book or just getting a computer to do it rather than doing what I'm doing, which is digital pen and digital paper. So this represents 18. The next one goes from 70 to 80, and that should be 14. So that's going to be here. I say 14, but it was a frequency density of 1.4. And then finally, we've got 0.7 for our frequency density. And that represents 7 carats. So the reason why this is a useful way of presenting the data is it gives a clear sense of what the distribution of weights looks like, which is a clue as to what the underlying distribution is. What I mean by the underlying distribution is the following. If I was to take a sample of, say, 1,000,000 carats and split it into lots of tiny, tiny, tiny class widths, this histogram will get smoother and smoother and smoother. And what I might see is a kind of overall smooth shape, okay, which maybe is this. Okay, something like this, which would give me a sense of how weights of carats were fundamentally distributed. And a histogram should give you an approximation of what that underlying shape was. That would be the shape if you had an enormous sample. So that's why they're really good. They preserve many features of that underlying shape. Let's jump over to Excel to see how Excel does histograms and look at some other techniques as well. So Excel is not really a good tool for creating histograms in the way that I just did then. It does have a histogram function, but has very limited control. Here's what it's good for. Suppose I have test scores of very, very many, hundreds and hundreds, maybe 1,000 students who've all sat a test, and I want to get a sense of how those results are distributed. I can select that data and I can insert what they're calling a histogram here. Now, the reason why this isn't actually a histogram is that the units up on the y-axis here are not frequency density. And also we have very little control. Like we can't have unequal widths. We can't, it's actually very difficult to even specify what you want these widths to be. You can do it if you say, for example, I want each of my bins, so each of these called a bin, for example, to have a width of 5. And I can have what's called an underflow bin here to say, well, let's just say anything under 45 will just kind of go into a less than or equal to 45 bin. Well, at least I can sort of slightly make sense of what these things represent. So I've got some neat categories here. I picked 45 because when I count up in fives from that, it gives me lots of nice, easy numbers to visualize. So Excel can do histograms. They're just not technically histograms, and you don't have very much control, but they're very useful for looking at how results are distributed. What I can see from this is that in these test scores, the majority of students achieve sort of 75, 80, 85. This is what we'd call a negatively skewed distribution, of course. And I can see there's a tail down here. So a small number of people really struggled. The majority found the test okay and achieved in that kind of region there. Okay, finally, I just want to show you what I mean about histograms preserving the shape of a distribution. I've popped over to a different program here. This is called GeoGebra. And what I've got is about 100,000 data points here. So just an enormous list down here of numbers. And I've plotted a histogram. And at this point, I've just got 5 boxes. And so that gives some sense of the shape. Now, if we increase the number of boxes, the idea with histograms is that however many boxes I draw, it should preserve the underlying shape. And what you can see here is that as I push on to around 20 boxes, the shape of the distribution is starting to become clear. In this case, it's the famous bell curve of the normal or Gaussian distribution. So this is what we mean by histograms preserving the shape of a distribution. In theory, however many boxes you draw, it should preserve the shape. And as for how many boxes you have, well, there are whole theories on what that should be, but basically, as many as you need for it to be clear what the shape of your distribution is. So that's what a histogram is. Technically, this is what, this histogram is something that can have unequal widths, and you calculate frequency density and area is equal to or proportional to frequency. More and more though, because Excel, which really kind of dominates how people think about visualizations of stats, doesn't really show a true histogram, it no longer quite has the same strict definition, but nevertheless, the key thing with a histogram is that the shape of the underlying distribution should be revealed by the position and height of the boxes of each individual histogram. Hope it's been a useful look at this interesting and slightly more complex data visualization technique. I'll see you in the next video. Next, we're going to look at box plots, which we did take a quick look at in the descriptive statistics chapter. We're going to look at them in more detail now. A box plot is a way of presenting your quartiles, your medians, your maximums, your minimums, your outliers, all in one graph, and a great way to compare these figures for two data sets. Let's have a look at how we create a box plot. So there are 5 bits of information at least 5 bits of information that you present on a box plot. So the things you need to work out are the minimum value, which is obviously really easy in this case since it's ordered, it's just 32. Our lower quartile, Q1. Our median, which you could call M, but we'll call Q2 here. Our upper quartile, Q3. And our maximum value, which in this case is 110. Okay, so let's work out the median. So I've got 10 values here. So the median is going to be halfway between the 5th and the 6th position. So remember, that's because if you have n data points, it's n plus 1. So 10 plus 1 is 11. Divided by 2, 5.5. So it's the 5.5th position, or halfway between 5th and 6th. So 1, 2, 3, 4, 5. The median is halfway between these two. So halfway between 55 and 61 is 58. So that's the median. The quartiles, we look at all the values on the left-hand side. I'm going to use the exclusive quartile system where I don't include, well, there isn't actually a median to include now, so it makes no difference. So I look at the values to the left of the median, these 5 numbers, and find the median of those. So that's 49, that's one in the middle there. So that's my lower quartile. And then my upper quartile is the middle value of these ones to the right of the median. So that's 63. So now that I've got those 5 data points, I can construct a box plot. All right, so the key features of the box plot are a box and 2 whiskers. Let me show you. We start with a dash at the minimum point. So the minimum point is 32. So I'm just going to put a small dash here. For the 3 quartiles, we put a longer dash. So that's at 49, which is here. At 58, which is here. That's the median. And at 63, that's the upper quartile, and that goes here. Okay, also the maximum value, that's 110, so that gets a small dash here. And then these 3 ones in the middle, these form our central box. And then we just connect these maximum minimum points with 2 lines here, sometimes called whiskers, sometimes called a box and whisker plot. So those 5 marks show us lots and lots of information nice and clearly. We have a box containing the middle 50% of the data. Remember, 25% of the data is less than the lower quartile, and 25% of the data is more than the upper quartile. And 25% of the data is included between the two, but 50% of the data is included between the 2 quartiles. So I can see really clearly that I've got 25% of the data in this little box, 25% of the data in this little box, so that's the central 50%, and the smallest 25% and the largest 25%. So that's how we construct a box and whisker plot. Now, I'm going to show you a box and whisker plot. I want you, for some different data, and I want you to see what the difference is. So spot the difference between that and the one I've just drawn. So take a look. So each of 60 students was asked to draw a 20-degree angle without using a protractor. So just estimating an angle. The size of each angle was measured and the results are summarized in the box plot below. So can we extract some information from this? Well, the first thing you might notice is that the whisker ends here and then there's a cross here. So sometimes, and this is sometimes done and sometimes not, sometimes outliers are represented as little crosses like that, and the whisker only goes up to a point beyond which you're classifying things as outliers. So maybe you remember earlier on in the course, I showed you that one definition for an outlier is one which is the lower quartile minus 1.5 interquartile ranges, anything beyond that point, so any x value that's less than that, or any x value which is greater, any data point greater than the upper quartile plus 1.5 interquartile ranges. So that's been used here. This end of the whisker around kind of 39 or so, that's the cutoff point, which we got using this formula, beyond which anything is counted as an outlier. So what can we extract from this box plot? Well, I can see that the minimum point is 9. That's easy enough to see. I can see that the lower quartile, Q1, well, that is 12. I can see that the median, Q2, is 16. I can see that the upper quartile is 25. And I can see the highest value is, I think, 47. So the maximum value is 47, but it was an outlier. So that's fine. If you see that kind of cross, it just means that the point was an outlier. It was beyond whatever cutoff point you're using. And it's not always going to be this condition, but this is just a common condition to use. Let's have a look now at how we can create box plots in Excel. So here's this data we've looked at before, where we've got sign-ups in different months. So the simplest way, if you just want to create a single box plot, you can just select the data that you want to put into a box plot. You can insert, and it's in this section here. We've got box and whisker plots. So, okay, that doesn't look too great. And one thing that we could definitely do is just alter the y-axis here. Now notice that they present them vertically. Yeah, there are options to change it to have it horizontally. Either is fine, really. But certainly, I think it's a little bit confusing to have it running from 0 to 90. I might just have it running from 50 to 90. And that looks a little bit better. So what we've got here is the minimum value, the maximum value, the upper quartile, the lower quartile, and the median running through the middle as well. So they also give you, by the way, the mean average for good measure. There's a little cross in there as well. So that's how you can create a box and whisker plot for one data set. They also give you the option to create a double one, which is actually a really nice way of comparing two data sets. So if we select the two data sets like this and insert box and whisker plot. Here we have the two of them. Once again, I'm just going to lose that. I think this is going to be clearer if we change this axis. We don't need it to run from 0 to 90. So to do that, we're just going to go to axis options here, vertical axis, and change them here. Let's go from 50 to 90 again. And now this gives us a really clear comparison between these two data sets, I think. Obviously, it doesn't show us changes over time. It loses that information, but it does show that across the year, Y, the sign-ups Y group, was generally higher, had a higher median, it had a higher quartile and everything, and it was less spread out, right? The fact that this box is smaller tells us there was a smaller gap between the upper and lower quartile, smaller interquartile range, so the data was less spread out. So that's a nice technique as well for comparing data sets. I hope that's been a useful look at box plots. In the next video, we're going to look at cumulative frequency curves. So I'll see you there. In this video, we're going to look at cumulative frequency curves, quite a creative way of displaying data and really useful in some situations. A cumulative frequency curve keeps track of how many elements in your data set there are up to and including different values. It's easy if I just show you in practice how we create one, and then you'll see what it's showing. Okay, so I've got data here on the angles drawn by a bunch of different students. So I've asked my students to try to draw, for example, a 70-degree angle. I've recorded what they actually drew and kept track of that here. So here's how we draw a cumulative frequency graph. So first thing I can do is I can say, well, look, none of my students drew anything less than 55. So I put a 0 down at 55 here. So it's 55 degrees, and my cumulative frequency is 0 because no one did anything less than or equal, well, less than that. 6 of my students did an angle which was between 55 and 60. So that means that 6 students drew an angle less than 60. Now, for these remaining ones, I need to think about cumulative frequency. So what's that? That is the number of students up to and including that point. So we have 6 students up to 60. Now we have 6 plus 15, so we have 21 students up to 65. And up to 70, well, it's the 21 I had so far, plus 13, that's 34 students up to 70. And the cumulative frequencies is, so it's the students up to 75 is what I had already, 34 plus 11, so that takes me to 45. Add the 8, I get 53, and add the 7, I've got 60. So here are my 60 students, and this is the cumulative frequencies. So I've plotted my first 2 points. So up to 65, I had 21 students. So at 65, I plot 21. So this is my next point on my graph. So the next one, up to 70, it's 34. So on 70, I plot 34. So that's here. Up to 75 degrees, it's 45. So against 75, I plot 45. And then up to 80, it's 53. So against 80, I plot 53. So that is 50, and there's 53. And then finally, up to 85 degrees, it was 60. So up to 85, here it's 60. And so there's my cumulative frequency points, and I just need to connect those in, not with straight lines, but in a kind of smooth a curve as I can do, which will surely be an easier thing for you to do with pen and paper than it is for me to do with my digital pen, so forgive me. And so this curve here is a cumulative frequency curve. It shows how the number of students grows as I look at how many students drew an angle less than or equal to various points. So I can read off this and say, well, how many students drew an angle less than 75? Well, it was that number there. So that's what a cumulative frequency curve is. Let's see how we could use them and what we can learn from them. So suppose I've got this. It says the examination marks obtained by 1,200 candidates are illustrated in the cumulative frequency graph, where the data points are joined by a smooth curve. So what could we use this for? Well, one thing we could do is we could extract information like the mean and the quartiles from it. So let's have a look at how we do that. Since I've got 1,200 students, the median candidate is going to be, well, it's somewhere between the 600 and the 601st. Since it's so many, we're just going to look at the 600th. So I can just draw a straight line out from 600 and a line straight down from there. And what I can see from that is that the median is 60. So what I've been able to do from that is extract Q2, the median, from the graph. I got a median of about 60. I could do the same with the quartiles. So the upper quartile is 3/4 of the way through my 1,200 students, so that's at 900. And again, draw a line down, and that's going to give me my upper quartile. So in this case, the upper quartile is about 70. And same thing for the lower quartile. So 300 is 1/4 of the way through my data. Draw a line down. So I get a lower quartile of about 45. Now, this is obviously not really accurate because I'm just estimating where these lines hit the x-axis, but it gives me a decent sense of where it is. Now, notice a quite kind of cool thing you can do. If you just extend these lines down and put a box there and some whiskers there, what you've got yourself is a box plot. So cumulative frequency graphs can be used to construct box plots. There's a strong relationship between them, which is kind of nice. Finally, you can use them the following way. Suppose I wanted to just select the top 100 students. And suppose I did not have an ordered list of all the results, I just had this graph. And I wanted to know, what mark did you need to get to be in the top 100 students? Well, what I could say is, of the 1,200 students, it's the students from 1,100 up, well, 1,101 up, technically, that give me my top 100 students. So if I draw a line across from 1,100 and a line down, that position where it hits the x-axis, which looks like it's about 78, well, 78 marks is going to be my kind of cutoff point. If I say I want all the students who got better than 78 or better than or equal to 78, that's going to capture roughly the top 100 students. So it can be used in these interesting ways. It gives a strong sense of how things increase, where the kind of majority of the data lies, and you can use it to extract some information. Now, Excel does not offer a kind of built-in cumulative frequency package, but really it's just a curved line graph, so we can sort of do it. I'll show you how. All right, so here's how we can do it in Excel. So here are all of my test scores, and I've got the kind of key points here. I could have set those to anything. I just decided to set them 10 apart, and I want a cumulative frequency tally. So a useful function here is the COUNTIF function. So if I say COUNTIF, open some brackets, I'm looking at this range, and what's my criteria? I want to count if any of these are less than or equal to each of these values. So the way to do this is a little bit weird, but we can say we put in quotation marks less than and equal, so less than or equal to, and that. Now, Excel will read that as count if anything in here is less than or equal to that value in C2. And none were, but as I drag this down, it will populate each one. So this one is saying, how many from this range are less than or equal to 80? And the answer is 430. So let's construct a cumulative frequency graph from these. So it's basically a glorified line graph. So if I select these and ask for a line graph, well, it's okay, but the orange bit is the one I want. The blue one is, well, it's trying to graph these. I don't want that. So remember how we lose those. We select our graph, then we say select data. I don't want the test score, that's these numbers here, to be graphed. So I click on that and I remove. But I do want my test score to be the x-axis. So I can edit the horizontal axis and select test score. And now we have the graph that we want. The only thing left to do is I would like this to be curved. So how do we do this? Well, if you click on the line itself, right click on that and select Format Data Series, well, you have some options here. Okay, and if you explore here and go to the bottom, there is the smooth line option. So if you click on that, then what it's done is it's slightly smoothed this out. And that's how you can create a nice looking cumulative frequency curve in Excel. You could do all the similar sorts of things we looked at before, like I maybe don't necessarily need this going all the way back to 0. I could start it at 20, for example. And I certainly don't really want this going to minus 100. So we could tidy that up if we wanted, like saying I'll go from 0 up to 900 there. And I could do the same thing here. But that's basically how we do it in Excel. It's a bit of a fiddle because they don't really have an inbuilt cumulative frequency graph, but we can do it. So that concludes our look through visualization techniques. In the next video, we're just going to sum things up by looking at the potential mistakes you can make when visualizing data and how to avoid these. So I'll see you then. We're now going to look at comparing different visualizations and thinking about some of the strengths and weaknesses of each one and some common errors that can be made in each case. So in this chapter, we've looked at a range of different visualization techniques, and we've seen that they're appropriate in different instances. So for example, if we are tracking changes over time, then a line graph or a bar chart is a good idea. When we're comparing proportions, pie charts are pretty good. If we want to visualize the distribution of data, then histograms are where we go. And finally, if we're visualizing the spread of data, then box plots and cumulative frequency curves do a good job. So we're going to look at a few of these and think about ways in which we can be misled by visualizations and what we can do to change that. So consider this. One common error when we're dealing with a bar graph is omitting the baseline. So have a look here. We've got some data and it looks very much like this group A is much bigger than group B and C. It looks more than double. And remember that your audience is often not going to take the time to carefully look through the y-axis here. And in this case, by omitting a 0 as a baseline, it makes it look like this group is so much bigger than the others, whereas in reality, that's not the case. Now, in this chapter, I've shown you some situations where you can do that. The key thing is, though, if it's proportions that you're trying to demonstrate, in this case, it's really the proportion between these we're trying to highlight, then it's really misleading. If we're trying to show how a single variable changes over time, then it can be a useful thing to do to just focus in on a certain part of the y-axis. But in this case, really misleading because it makes it look like group A is significantly larger or whatever being measured than group B and C. Okay, so let's have a look at another example. So here's something that was published, a percent who agreed with court, and it's split up by party in the United States. And you can see that what's really what's misleading about this, right, is that it makes it look like the Democrat cohort was much bigger than Republicans and independents. And in fact, when we take the time to look at the y-axis, we see that's not the case. And so the correct graph would be something like this. Okay, here's another example of omitting the baseline. This is data from Spotify, I think, and it's the kind of top listened to or top streamed artists. And again, they've omitted the baseline, and it's really hard to see that here, but it looks like the artist up at the top, Drake here, has more than twice as many listens as artists down here. But actually, if you look at the numbers here, you see that's not the case. So this would be a more accurate representation. And now we see that, okay, it is more, but it's not that much more. The baseline here gives some indication of what the true reference points are, particularly when we have 0 as a starting point. Okay, another graphing error and how we can correct it is manipulating the y-axis. So the reason why this is misleading is by displaying y values all the way from 0 to 40, it makes it look like these changes are quite small. So showing a really large area where most of it's empty can disguise changes. When we instead zoom in on the 0 to 15 mark, we see that these changes are actually quite big as a proportion. So this almost looks flat across here at first glance, whereas here we can see it's not flat. So here's another nice example. So this is the average annual global temperature in Fahrenheit over many, many years. And the y-axis scale takes us from 0 to 120. Now, obviously, the average annual temperature doesn't vary much on that scale. And when we plot it like this, it looks like it's been basically constant, almost a perfectly straight line. But when we zoom in, we see this result, right? So if you're interested in changes in global temperatures, you might want to zoom in onto a scale in which you can see changes, right? So once we do this, we can see, no, there has been a change from approximately 57 rising up to approximately 58. And that kind of change is completely concealed by this graph here. Okay, sort of creative example of manipulating the y-axis, not really the y-axis here, but manipulating the dependent variable, if you like. So here's a screen grab from a credit rating score. And so the score is 634 out of 700, but they're setting this up on a sort of speedometer chart. And so I've got this green bar here, which I'm hoping is going to increase all the way around to here. Now, the fact that it stops here makes it look like I've got a long way to go. But 634 out of 700 is pretty good. It's like most of, in fact, it's more than 90%, but they've not shown 90% of the way around the circle in green. So, maybe a more accurate way to do it would be this, where this green bar is shown to be what it really is, which is over 90% of the way around the circle. So there's another creative use where this company, they want you to believe that your credit score is low so that you use their services to improve it. And one way they do that is by stopping the green line here, rather than showing that you're actually very close to a full score. Right, here is our third way in which we can make errors, and that is cherry picking data. So whatever this is misleading, if I looked at this graph, I would think that whatever's being measured is increasing. And this is measurements from May 2020 to August 2020. But if I look at a bigger time frame, what I see is, okay, it's increasing and then it's decreasing. So cherry picking data might be if my narrative was that the thing that I'm measuring is increasing, I could show this graph. Now, if I just cherry pick the region in which it is increasing, it's basically a lie. At least like the overall picture that I'm selling or overall story that I'm selling is not one that's reflective of reality. So we want to avoid just picking out the section that tells a story that we want to tell. Here's a nice example. Here's UK national debt as a percentage of GDP. And if I look at this, it looks like it's going up, right? And so if the story I want to tell is that GDP, that national debt as a percentage of GDP is increasing, this is a graph I could show. But if I look at data on a much longer time frame, what I see is that, in fact, the trend is of many, many years of decrease with a little increase at the end. And this region here is just plucking this data out of it. Now, that's okay as long as you're crystal clear that this is in recent years. But obviously, we've cherry picked out the part that tells a story that we want to tell when the bigger picture of a story is of a story of decline. Okay, a fourth way in which we can mislead with our visualizations is using the wrong graph. So here I've got team A, B, and C, and maybe this is about, how many people have a favorable opinion of, or how many people support, or something like that. And what's clearly wrong about this is that these percentages don't add to 100. So clearly that people who responded, or the data we gathered, it wasn't you had to pick either A, B, or C. Clearly there were options to pick more than one. We don't even know what was being measured, but a pie chart is definitely not the way to visualize this data. It's very, very confusing if we see these because we expect pie charts to have the percentage of the circle taken up. And so if it's something else being measured where they don't need to add to 100, well, this is the way to show it. For example, maybe this is the percentage of games won or something by 3 different teams. And here we can clearly make the comparison. We can clearly see which team's better. Team B seems to be the best. The pie chart is just incredibly confusing. So if you're including percentages on a pie chart, they better add to 100%. How about this? Microsoft Edge are trying to show how fast their browser is, and they've decided to go for a sort of speedometer view, and it's just really, really confusing because these speedometers are not set from 0. Basically, other than them just telling me that it's faster than these other two, I can't really tell how much faster without just looking at the numbers, in which case the visualization didn't really do anything. So much more boring, but a much more accurate view would be this. And now I can accurately see, okay, Edge, at least according to their data, is faster. How much faster? Not very much. Now, that's obviously just not the story they wanted to tell, but if we want to be sincere in our analysis, then we want the visualization which gives people a true reflection of what's going on. So here's a fifth and final and slightly subtler way in which we can mislead with our visualizations, and that's going against convention. So a convention, which you may or may not be aware of, is generally we use darker colors to represent larger numbers and lighter colors to represent smaller numbers. Now, whatever this is measuring, it says individuals per kilometer. I don't know if that's people or I don't know what it's measuring. But the point is, This is when people look at this, they're going to see a light color here and assume that means a lightly populated or whatever it is, a small number versus a large number in the darker uh, uh, colored states here. But that's not actually what's being shown. So according to our scale, the dark colors represent small numbers and the light represent the larger numbers. But that's not what people are going to expect. So sometimes being aware of what those expectations are involves talking to other people, showing them this, maybe without the axis, and saying, okay, when you look at this, what do you think it's showing? Like, which do you think are the higher numbers, and which do you think are the lower numbers? And sometimes you'll see there is a consensus, even if people weren't aware that there was. So this would be the correction where the darker shading represents the higher number. Here's another example. Here's a kind of crazy graph I found. So this is gun deaths in Florida. Now, it takes a while to figure out what's going on here, but they have inverted the y-axis, which is clearly going against convention, right? We always expect the y-axis to be increasing. It's incredibly confusing to see it. The higher we go, the smaller the number. And I mean, this is done for cynical reasons. It's to show about some intervention here, followed by what looks like a drop. But obviously, that's not a drop, it's an increase because down means up on this graph. So don't go against convention, right? We expect the higher up on the y-axis is to mean the higher the number. So what's the solution? Well, I've just sort of reflected and rotated this, and this is the actual shape of the distribution. So we see there was intervention followed by increase. So think about what conventions are. If you're not sure what the convention is, check with someone else. Show someone else your visualization, see if it's confusing. So I hope you've enjoyed looking at data visualizations with me this chapter. I think the overall message is be creative, but overall be clear and truthful with your visualizations. Create something which helps people understand the data quickly and clearly without misleading. That's all for now. I'll see you in the next chapter. In this chapter, we're going to look at sampling. Sampling is an incredibly important skill for a statistician. I've already talked earlier in the course about the importance of knowing the distinction between a population and a sample. And in this chapter, we're really going to dig into this and look at some techniques we can use for taking samples, how we do it, and what are the costs and the benefits of each one. So in this chapter, we're going to be looking at three things. First, we're going to look at populations and samples, looking at what a population is and what a sample is. Then we're going to look at some random sampling techniques. And finally, we're going to look at some non-random sampling techniques. Let's begin by looking at populations and samples. We're going to begin by looking at what a population is. So we typically think population means the number of people or the group of people who live in particular countries. But statisticians don't mean that when they say populations, at least in general. We can talk about the population of a country, but it won't always be that. So here are the definitions. Population is all elements of the group that you want to draw conclusions about. And a sample is a subset of the population that you will gather data from. So we're going to look at a few examples now to spell out exactly what that means in a range of different contexts. So let's think about this. Example one, you want to know the average weight of a grain of sand from Hawaii. Now, I don't know why you want to know that, but you do. So what is the population here? The population is every single grain of sand on Hawaii, right? Because the population, by definition, is all of the elements of the set of things that you want to draw conclusions about. I want to draw conclusions about grains of sand from Hawaii, so my population is every single one of them. Okay, another example. You want to know the strength of pieces of rope produced by a particular machine. So what's the population? It is each piece of rope ever produced by the machine. So this is certainly every piece of rope produced in the past up to the present. Maybe it could even include the future as well. Finally, you want to know which candidate people will vote for in an upcoming election in Berlin. What's the population? It's every person eligible to vote in the upcoming election in Berlin. Okay, so now that we've seen some examples of what populations are, we're going to go back through those and think why in each case we might need to take a sample if we wanted to learn about whatever it is we want to learn about. So in this case, where we want to know the average weight of a grain of sand from Hawaii, well, the population is every grain of sand on Hawaii. So why do we need a sample? Well, you can't realistically measure the weight of every single grain of sand on Hawaii and find the average, clearly. So population is far too large to gather data from all of it. In fact, it is considered an infinite population. So this is a terrible bit of statistical jargon. So an infinite population in statistics is one in which it is practically impossible to list all its elements. Clearly, there are not infinitely many grains of sand on Hawaii. It's just the number is too large to list. So if you have some kind of population which the elements can't possibly or easily be listed, statisticians will sometimes call it an infinite sample, an infinite population. And if you have an infinite population, well, you definitely need to take a sample if you want to learn more about it. Okay, what about the rope? So remember, our population here is each piece of rope ever produced by the machine. So why do we need a sample? Well, some pieces may not be available, right? They might already be sold, they might be broken, they might not even have been produced yet. And the other reason is that maybe the acts of measuring how strong a piece of rope is involves increasing the amount of force that it's taking until it breaks, right? So if you were to measure every single element of the population, it might involve destroying every single rope that you have. So there are many situations where you would just never want to test every element in the population. So that's why we need a sample here. Lack of availability and also the act of measurement might destroy the item. Okay, finally, we've got our who people are going to vote for in an election in Berlin. So why so why might we need a sample here? Well, it could just be very expensive and time consuming to make contact with everyone eligible to vote. And this is probably the most common, if dull, reason why we need samples. That measuring, like taking measurements, right, recording data is very expensive and time consuming. Right, Berlin, the population of Berlin is into the millions, I think. And so it would be essentially impossible, but certainly extremely expensive to go and sample every single person. That's not possible, whereas a sample is manageable, and also a good sample can be very representative of the population. More on that in upcoming videos. So that's what a population is, and that's what a sample is. Now that we've seen that it's often impossible, in fact, usually impossible to work with every element from a population, we're now going to turn our attention to how to take a sample. The key idea being we want our sample to be representative of the population. So the next two videos, we're going to look at some ways to do this. I'll see you there. Having looked at the definition of a population and a sample, we're now going to look at how we take a sample, focusing first on what a random sample is and a few different techniques on how we do it. So suppose we wanted to take a random sample of our grains of sand in Hawaii. Well, how would we do it? Well, the answer is we can't do it. And the reason we can't do it is we don't have something called a sampling frame. So a sampling frame is a list of all elements in the population, because a truly random sample is one where you take your full list of the population and then you randomly select elements in that list. And if you don't have the list to begin with, you're not doing a truly random sample. We'll look in the next video about how you take a sample that is as representative as possible in this kind of situation. But for a truly random sample, you need the list. So let's take an example of where we could do that, and that's our election in Berlin. So if we wanted to sample the eligible voters in Berlin, we would start with a list of all of them, and that's presumably doable. You could find that. Maybe it's just the phone book or something like that. So here's our the kind of first 20 names in our list of people in Berlin. And to take what's called a simple random sample, the process is this. You first number all of the elements in your list. Then once you know the size of your population, so in Berlin it's just over 2 million, you then generate random numbers in that range, and and you keep on generating them until you've got the number you want in your sample. So here are some random numbers in that range I generated, and then you match those random numbers with the elements in the list with those numbers. So I'd look down in that list and I'd match them against these people here, for example. And that would be my random sample. And that method is called simple random sampling. Now, in reality, we often do this a slightly different way. I'm going to show you a technique in Excel now of how to take a random sample, and it is still simple random sampling. It's just a bit easier to carry out than this method I've shown you here. So here is a long list of names. I'm not sure how many people are on this list, doesn't really matter. But suppose I wanted to take a random sample of 10 of them. I wanted to use a technique of simple random sampling. Here's one way I can do it. I'm just going to add a column above to say, here are the names. And I can use Excel's random number function to help me. So here's going to be my random number. And the formula you're going to need, you press equals and then rand, open bracket, close bracket. There's no input within those brackets there. And that's going to generate a completely random number. Well, it's pseudo-random because it's a computer doing it, but it's as good as you can get to random. Number between 0 and 1. If I double click here, it's now sending them all the way down the list. And each time I click F9, it regenerates these numbers for me. So it doesn't really matter. Of course, it doesn't matter what they are because they're random. But what you can do now, if you want to select a sample, is if you click on data and you filter, you can order your data by these random numbers. And so that will be a completely random ordering. And then you can just select the top 10. So if I sort these from smallest to largest, it doesn't matter, or largest to smallest. Okay, now the ordering's now wrong because it's regenerated them. But the point is, it doesn't matter. It ordered them on what they were before, and that was a random ordering. And so here, if I just take the top 10 of these, that is a completely random sample from my list. And so these people here, well, that would be a random 10 people from my full population. And this is simple random sampling. So let's look at some of the pros and cons of simple random sampling. So a clear pro is that there is no bias in this, right? The method itself includes no bias because it's truly a random process. It's quick, easy, and cheap in the sense that I just generate some random numbers. There's no other thought or process behind it. So it's very easy, it's very quick, and it doesn't really cost anything. And each item is equally likely to be picked. Again, that's similar idea to there being no bias, not quite the same, but each item is equally likely to be picked. What are the cons? Well, we need a sample frame, so we couldn't do it for our grains of sand in Hawaii. And also, it doesn't guarantee that the sample is representative. This is particularly a problem if you have a very small sample. For instance, if you had a large population in which 50% of the people were men and 50% were women, and you took a small sample of, say, size 10, it's not out of the question that you end up with 8 women and 2 men, for example, or vice versa, or some other imbalanced sample. So if it's very important that your sample is representative of the population, well, we have a technique for that, which I'll show you later on in this video. But simple random sampling, because it's a completely blind process, does not guarantee that the sample is representative. Okay, our next technique is systematic random sampling. I'm going to show you how to do this one in Excel. So a systematic random sample differs from a simple random sample in the following way. Unlike a simple random sample, we just generate numbers randomly or randomly sort our data. A systematic sample does the following thing. First thing you need to know is how big your population is. So I've already checked that, it's 519. So let's just keep track of this. That's the population size. And our sample size, well, I'm just going to try to select a sample of size 10. So first thing to do is work out the gaps between our position sample. And you'll see how we use this in a second. So my gap can be found by taking the population size and dividing it by the sample size and then rounding this to the nearest whole number, which in our case is 52. Then we need a randomly generated starting position somewhere between our first data point and our 52nd data point. So our starting position then is going to be, and I can use Excel's function here, a random number between, so I can use the round between function, and since my name starts at 2, it's going to be between 2 and 53, because that includes 52 names. Okay, so that was 50. Okay, I'm just going to type over this so it doesn't regenerate. So I've got everything I need now. Once you've got your starting position, you just take that and you add your gap, which for us was 52. And these then are your numbers that you're going to be sampling. And we do that until we have a sample size of 10, which we do now. So in this case, that was my starting position was 50. So this person was going in, and that was the randomly selected starting position. And then I go 52 later, and so that was this person. And then I go 52 later, and that was this person, and so on, until I have my sample. And these numbers here tell me their positions, and then I just find the names associated with those. So that method there is called systematic random sampling. Okay, let's have a think about some of the pros and cons of systematic random sampling and compare it to simple random sampling. So the pros, it is quick, easy and cheap. It also very easily generates samples from a large population. It can be quicker and easier, particularly when your population is very large, to use a systematic approach rather than the simple approach. Because sometimes just the random number generation, the hunting around for those numbers, can be a laborious process, whereas just knowing a random starting position and then a constant gap between each term can make it easier to generate a good enough random sample. Now, what are the cons? Well, a sample frame is needed, just like it was with simple random sampling. And then finally, and I think this is the interesting one, it can introduce bias if the sample frame is not randomly ordered. Take the example of the names, okay? And let's say that we were maybe considering the list of people in Berlin, for example. Well, if we have a constant gap, it means that we're never selecting two people next to each other on the list. Now, what does that mean? It means you're never going to select two people with the same surname. So, for example, you're never going to select, for example, people in the same family, like two people who are married with the same surname, or brother and sister with the same surname, or cousins with the same surname. Now, that might be fine, but it also introduces bias because the population includes siblings or married couples or people with the same name. And if your sample actively ensures that you don't have that, it can introduce a bias. In this case, for example, it may lead you to draw conclusions about the population that wouldn't be true if some elements from your sample did have the same surname. This is just an example with surnames. But having a constant gap does sometimes mean that you fail to capture some aspects of your population, but that's in cases where your sample frame isn't randomly ordered to begin with. The final form of random sampling we're going to look at is stratified random sampling. So take this example here. Suppose that we had a company and its employees' ages were known and they were in these categories. Now, suppose that I wanted to select a sample and it was my population size was 240 and I wanted a sample of size 30. And it was very important to me that my sample reflected the age distribution of employees across the company. So here's how we do it. We first work out how much larger our population is than our sample size. So that's as simple as just saying, well, we've got 240 in our population. divided by the sample size, and that's 8. So our population is 8 times larger than our sample, and conversely, our sample is 8 times smaller than our population. So to find the sample that we're going to take from each category, we're just going to divide by 8. So I then take that number and I divide each of my frequencies in each of the strata, as they're known, by that scale factor. In this case, that was 8, right? My sample is 8 times smaller than my population. So I take 49 and divide it by 8, and the nearest whole number is 6. So we can just round to the nearest whole number. 63, well, in that category, I'm going to divide that by 8 and get 8. So I'm going to sample 8 people from that category. And I keep on continuing all the way down, and these numbers here then tell me how many people to sample randomly from each of these. And so within each of these categories, I then use a random sampling technique, simple or systematic, to sample this many people. And so that process ensures that my sample will be representative, at least with regard to age, across this company. So what are the pros and cons here? Well, it allows small samples to be representative, at least in the domain which I'm focusing on. So if it's age, it allows it to be representative by age. It does guarantee samples will reflect the population in the selected categories. Cons? Well, population must be classified into strata to begin with. It can still be unrepresentative in other dimensions. So I was looking at age, I wasn't looking at gender, for example. So we might end up with a sample which is not representative of the company in gender. And selection within each strata is still subject to all of the issues of random sampling techniques in general, because once we know how many we need from each strata, it is just simple or systematic sampling, random sampling once we're there. Okay, I hope that's been a useful look at random sampling. You see there are 3 different ways we can do it, all with their own strengths and weaknesses. In the next video, we're going to look at some of the non-random sampling techniques available to us. We're now going to look at some non-random sampling techniques, and these are great in instances where random sampling techniques are not possible. So consider this case again, where we're interested in the average weight of a grain of sand on Hawaii. So we've seen that a random sample is not possible because no sampling frame exists. There is no list that exists or could be made of every single grain of sand on Hawaii. So we cannot truly randomly select grains of sand to measure. So we're going to have to use non-random sampling techniques. And these are fine. People use these all the time, and if we're careful, we can still get a representative sample. Remember, that's the aim, is to get a sample which is representative of the population. So the first one I'm going to talk about is opportunity sampling. So that is selecting any element from the population during the process of gathering data. So what would that mean in the case of measuring grains of sand in Hawaii? Well, it might just mean walking onto a beach, picking up a few grains of sand and weighing them. Maybe you'd make sure that you went to a few different beaches to ensure it's representative of sand all the way across Hawaii, but it's basically that. It's sampling the data that you have the opportunity to measure. So in this case, just going to the beach, picking up some grains of sand and measuring those. So that's opportunity sampling. It could be, if you want to know about people in Berlin, just walking out onto the street and asking people you come across. So these are examples of opportunity sampling, where you don't predetermine the measurements you're going to take. So it's not that I had a list of people in Berlin to go and find. I just went out and asked people, and anyone who gave me an answer, that was a data point. So this has some clear disadvantages, but it has some clear advantages as well. So it's very easy to carry out. You do not need to prepare your sample in advance. No sample frame required. The cons, it's obviously very easy to introduce bias. In the case of grains of sand, you may only go to certain beaches, right? You might always be going to beaches on the west coast or the east coast, which could change the result. You might, in your selection of grains of sand, be drawn to the big ones. You might only be able to pick up the big ones. In the case of elections in Berlin, maybe you're so intimidating that the only people who dare to answer your questions are I don't know, people who are very brave, and then your sample is of brave people in Berlin, not normal people in Berlin. Could be all sorts of things. Maybe you approach certain types of people. By walking out into the street in Berlin, you are biasing your sample to only include people who go out on the street in Berlin, so not people who are at home or working. So it's extremely easy to introduce bias into this. So that's something to be very careful of with opportunity sampling. One way that you can reduce this is with something called quota sampling. So it's similar to stratified random sampling, but without the randomness. So you set a particular number of desired samples in each group and then use opportunity sampling until each group is filled. So suppose that I was interested in recording some data about students in a school, and I knew that they were aged 14 to 18. Now, one way in which I could bias my sample, if I just use very simple opportunity sampling, would just be walk out in the playground and ask people. And how does that introduce bias? Well, maybe it's only the 14 and 15-year-olds who are out for lunch at that point or something. So one way to get around that is to set a quota for each of my categories. And then I just walk around sampling students, asking their age, recording whatever it is I want to find. But once I have 10 14-year-olds, I now don't take any more data from 14-year-olds. Once I have 10 17-year-olds, no more data from them. So ensuring that I fill these quotas ensures the sample is more likely to be representative, at least on the dimension that I've controls for, in this case, age. So here are the pros and cons of this. So it allows small samples to be representative much more easily than simple opportunity sampling. It's quick, cheap, and easy. And again, no sample frame required. Now, cons, bias can be introduced if sample sizes are not correctly set. So if, for instance, in this school, there may have actually been far more 14 and 15-year-olds in the school than 18-year-olds. And if I didn't know that, well, I've now skewed my sample because there are proportionally too many 18-year-olds and proportionally not enough 14 and 15-year-olds. So you can unintentionally introduce bias if you don't set your quotas up correctly. Now, furthermore, some groups may be harder to sample than others. In fact, it may be impossible to fill your quotas. So it's a process which, in certain situations, may not be possible, right? If you just don't manage to fill a certain quota, then you haven't actually achieved what you set out to do. All right, so we've now looked in this chapter at populations, what they are, why we often need a sample, and then what some of the most common random and non-random sampling techniques are. It's a very, very important area of statistics. Finding a sample which is representative of the population is often half of the battle when doing statistics. Anyway, I hope that's been useful and enjoyable. I'll see you in the next chapter when we're looking at probability. In this chapter, we are looking at the fascinating world of probability. It's one of my favourite parts of statistics. It's deeply satisfying, often unintuitive, and lots of fun. So let's see what we're going to cover in this chapter. We're going to start off by looking at the slightly unusual question of what is probability. If we don't know what it is, then it's going to be hard to make sense of what follows. We're then going to look at set notation. We need to get the notation down so that we understand what everyone's talking about. Then we're going to get into some of the theories and techniques. So we're going to start by looking at what independent events are and how we can model them. Then we'll look at mutually exclusive events, how to model and represent and calculate with those. Then we look at a few different common techniques. So we're going to learn how to use tree diagrams to solve probability problems. We're then going to look at Venn diagrams and see how and why and when they're useful. Then we're going to look at conditional probability, where things get a little bit more advanced, also more interesting. And finally, we're going to explore the fascinating world of Bayes' theorem. Let's begin, though, by answering the question, what is probability? If I asked you the question, what is the probability when I roll a dice that I roll a 6? You probably know the answer. Assuming it's a fair dice, the probability is 1/6. What do we mean by that? Well, there are two common explanations for what we mean when we say that the probability is 1/6. So one of them is what we might call something of an objective approach, which is that the reason why all people, if they understand the question, will believe that the probability of rolling a 6 on a fair dice is 1/6 is because that is indeed the answer. Now, why might they think that's the answer? Well, one reason why it could be the answer is the following. If I rolled a dice, maybe another dice, maybe I rolled a million dice, I might find that the relative frequency of getting a 6 is 1 in 6. Right? If I rolled a billion dice 1/6 of the time, it would be 6. And the more dice I rolled, the closer the probability would become to that number. So that, in a sense, is an objective approach of how to describe probability. You look at the frequency of an outcome if it's repeated essentially infinitely many times. So what could be a different approach? Well, a different approach, which is maybe a more subjective one, is to say that it's not to do with any fundamental properties about it, but about what information you have about it. And each person may have different information. Now, this is actually the definition of probability that I'm going to work with, but I do understand it seems unusual. And I'm going to be careful here to try to explain why it's not subjective in the sort of, well, you could choose to think that the probability is whatever you want. It's subjective in the sense that it's based on the information that you have. Now, in the jargon, you'll sometimes see these described as the frequentist or versus the Bayesian approach. I'm going to be taking a Bayesian approach in this course. The frequentist one says a probability is just the long-term relative frequency of an outcome. The Bayesian one roots it in the kind of degree of belief that you are rationally justified in attributing to a certain outcome. So for rolling a dice, the thing is, both these approaches yield the same outcome, right? I am rationally inclined to believe that there's a 1 in 6 chance that this lands on a 6, and so is everyone else. So it's not a particularly interesting case. More interesting case would be something like this. Suppose there were an upcoming horse race, and I wanted to know what's the probability that this horse here was going to win the race. Well, what could the frequentist say about this? Well, the frequentist approach is slightly odd because they would need to say, suppose that this race was run sort of many times, well, you'd count the number of times that this horse wins the race, and you'd divide this by the number of times that the race was run. So how many races were there? And that this probability here, at least when we approach infinity, that's the probability this horse wins. Now, an obvious problem with this is that it really makes no sense with something like a horse race to talk about it being repeated many times, infinitely many times. This is an event which happens just once. It's not like a dice, which could potentially be rolled infinitely many times. It's a one-off event. It happens only once. So this calculation here doesn't make much sense. So there's one reason why the frequentist approach logically may not make a whole lot of sense. Let's look at another example, I think, which is even more compelling for why the idea of probability as subjective degree of belief is so compelling. Okay, so suppose that me and my wife are expecting a child, and we don't know if the child is a boy or a girl. And I say to this guy, who's my Uncle Alan, I say, what's the probability that my child is a boy? And he might reasonably say 50%. I mean, he's got no idea, so that's a very reasonable thing to say. Suppose I then ask the same question to Dr. Anna. So, Dr. Anna has just been carrying out some research on the area where I live and has found out that for the last few years, in fact, 51.2% of children born are boys. So she says she thinks the probability that my child is a boy is 51.2%. So is she right and is Alan wrong? I mean, Alan doesn't know that fact. So is he wrong to say 50%? I think people have mixed intuitions about this, but I would say it's reasonable for Alan to say 50%, given that he doesn't have that further piece of information. Let's hammer this home with the following case. Suppose that this person here, midwife Sarah, well, she's just done a scan, and her scan suggests the child is a boy. And so she says she is 95% positive that the child is a boy, because let's say her equipment gives the correct answer 95% of the time. So how do we interpret this? Is she right and is Anna and Alan wrong? I think most people would be unwilling to say that Anna is wrong to say 51.2%. Remember, Anna hasn't seen the scan that Sarah has done, and Alan also has not seen the scan that Sarah has done. And I would agree with this. I would say that each one of these people is correct because they are all giving an answer which is rationally consistent with the information they have. So that's the subjective Bayesian approach. It's subjective not in the sense that anyone can believe what they want. So it would be irrational and actually wrong for Alan to say he's 90% certain it's a boy just because he has a hunch, because a hunch is not a rational bit of evidence to base a belief on. But since he has no other information, 50% is a rational response for him. Since Dr. Anna has the additional bit of information, slightly more children born of boys than girls, she can rationally say 51.2%. And since Sarah has actually now done a scan, which is correct 95% of the time, she can give a more confident answer. And I think the correct interpretation is that they are all correct. They are all stating a probability consistent with the information they have. That's the Bayesian approach then. What is probability? It is rational degree of belief. It's what you are rationally allowed to think based on the information that you have. Okay, so now that we've looked at what probability is, the rest of the chapter we're going to get on and work out how to calculate probabilities. In this video, we're going to look at set notations. This is the terminology that we're going to be using throughout this chapter for writing probability statements. Let's begin by looking at a bunch of characters, some of whom are dogs and some of whom wear glasses. So here they are in all their glory. Now let's organize them in the following way. I'm going to put them in what's called a Venn diagram. And this is useful because I can see that all the characters who are dogs are in this bubble here. All the characters who have glasses on are in this bubble here, and everyone else is on the outside. Let's begin by looking at what a set is. So a set is just a list of elements. So my set D, standing for dogs, let's say, the set, that set is just all of the dogs. Okay, so if you see kind of curly brackets around something, it tells you that we are listing out the elements in a set. So it is just those dogs. That is what the set D is. What about this? Well, G for glasses is just all of characters who wear glasses. So that's just what we mean when we talk about a set. What about the set of dogs who wear glasses? Well, this is how we write it. So that symbol there is called the intersection symbol. And intuitively, you can think of it as an and. So that's D and G, or you could say D intersection G if you like. So which characters is that? Well, it's just this guy in the middle here, because he is the only one who is a dog who wears glasses. We could then start to think of probability statements. For example, P, D, and G means what's the probability that a randomly selected character is in this set. So what's the probability that a randomly selected character is a dog who wears glasses? Well, we just need to count the number of characters who meet that description. There's only one, and divide by the total number of characters, which is 12. So 1 in 12 is the probability of D and G. 1 in 12 chance you select a character who is a dog who wears glasses. What about dogs or characters who wear glasses? Well, it's this symbol here. Intuitively, that's OR. So it's D or G. Now, the correct technical term for that is union, so D union G. Importantly, it's the inclusive OR. It's dog or glasses, or both. So we always include the both. And we could then think about probability statements. So the probability that a randomly selected character is either a dog or a character who wears glasses, or both. Well, we count how many there are. So there's 7 because it's either this dog, this dog, this dog, this glassware, this glassware, this glassware, this glassware. So there are 7 characters who meet one or both of those. And we can divide that by 12 because there are 12 characters in total. So that's the probability of a character being either a dog or one who wears glasses. Okay, what about characters who do not wear glasses? So we put this kind of dash there, and this is technically called the complement of G. It's the set of all elements who are not in G. So it's all the characters who do not wear glasses. And again, we can make a probability statement. So how many characters are there who don't wear glasses? Well, 1, 2, 3, 4, 5, 6, 7. So there are 7 characters who don't wear glasses. So the probability of randomly selecting a character who does not wear glasses is 7 out of 12. So that's how we can write these probability statements using those kind of symbols. And here's a little recap. So we've got our A intersection B, which you can intuitively think of as A and B. We've got our A union B, which is A or B or both. We always mean the inclusive or. It's never A or B but not both. It's always A or B or both. And then we've also got our complement. So A dash means the complement of A, which is not A. Okay, let's have a look at how we might represent these. So I've got a bunch of Venn diagrams here. Let's try to describe the shaded region in each case. I'd encourage you to pause the video here and try to complete this yourself. All right, so starting with this one here, what's this? Well, the shaded region here is the overlap between A and B. So that one there is simply A intersection B, or A and B. The shaded region is the bit which is both. How about this? Well, here we've got A or B or both. So this is just A or B, which is A union B. What about this one? Well, in this one at the bottom, everything is shaded apart from A. Well, that means that we're dealing with the complement of A. This is not A. Everything that's not A has been shaded. Okay, let's try some harder ones. And again, definitely try these if you dare. Okay, what about this one at the top? Well, everything has been shaded apart from our A or B region. So here's how we can write this. So the bit that wasn't shaded is A or B. But the bit that is shaded is the stuff which is not that. So here's one way that we can write the solution to this. Now there's actually a second solution as well, which is not A and not B, because this region on the outside is the intersection of the stuff which is not A and not B. It's the region which isn't either of them. It is not A and it's not B. Okay, what about this? Well, we've got B, but not the stuff which is A. So it has to be B, it can't be A. So we can write that in the following way. We can say it is B and not A. Okay, so this ensures that it is B, but it's definitely also not the stuff which is in A, which loses us that bit in the middle. So yeah, B but not A, that but not logically is very similar to just and. B and not A. Okay, how about this? So this is the exclusive or. So it's A or B but not both. So how can we write that? Well, we can say it's A or B, but it's not A and B. So I can say and not A and B. So A or B, but also, so and not A and B. So that's a kind of a much more complicated one there. That's our exclusive or A or B, but not A and B. Okay, let's have a look at some three-way ones. So again, pause and have a go yourself if you can. So what have I got here? Well, I've got A, and I've also got C, but definitely not anything that's in B. So this is basically our union of A and C, but with B removed. So let's start with our union of A and C. So that's A or C. So that includes everything in A and C. So it's all of that, but it's not the B stuff. So I want and not B. Okay, so I do want it to be in A or C, but I also want it to definitely not be in B. And so that and not B snips out the B stuff. Okay, hardest one down here. So we definitely want it to be all of C. And then we want the rest of A, but not the B stuff. So let's start with the kind of the rest of A, but not B bit. Well, I can do that by saying A and not B. So that would be this sort of crescent in here. So I do want that. And then I'm also happy to have anything that's in C. So it's this region or C. I think that's going to get me exactly what I want. So that's C, so all of C, or anything in A that's not in B. So C or anything in A that's not also in B. The last thing I want to show you is the empty set. So suppose I wanted to consider something like the intersection of A and not A. So something and not itself. So that's like a number which is, I don't know, as the set of all numbers which are even and also not even. Well, there aren't any. So what is a set that contains nothing? Well, it's the empty set. And the notation for the empty set is 0 with a cross through it like that. So when something is impossible, right, when there's no overlap of two sets and you ask for intersection, it's the empty set. So the empty set, by definition, is the set with nothing in it. Okay, so that concludes our little intro to set notation, how we reference it on Venn diagrams. So I hope that's been fun, and I'll see you in the next video when we're going to be looking at calculating probabilities. See you there. We're now going to look at independent events. So some examples of independent events would be rolling a 6 on a fair dice, that's event D, let's say, and flipping heads on a normal coin. So we know that rolling a 6 is a 1 in 6 chance and flipping heads is 1 in 2 chance. Now, these events don't influence each other at all. So if we look at all the occasions in which we roll 6 on a dice, that's 1/6 of the time, on half of those we would also have flipped heads. So it's pretty natural and hopefully intuitive to see that we're going to multiply these probabilities together if we want to know the probability of both of them happening. So in this case it's 1/12, and that's calculating the probability of D and C happening. So we can generalize this and give the following definition of an independent event. And this is an if and only if definition. So let me read it and then explain. Two events A and B are independent if and only if the probability of A and B, it's their intersection, the probability of them both happening, is just the probability of one multiplied by the probability of the other. So it's if and only if, which means it runs both ways. So if they're independent, then that you can use that formula. And if that formula holds true, it means they in fact are independent. So intuitively, we think of independent events as being events which have no effect on each other. But there is a formal statistical definition, which is this. And so there are many situations where we don't really know if events influence each other in any way. But if this condition holds, then they are statistically independent. So this is sometimes referred to as the AND rule because it's the probability of A and B. Just remember that it's not a general rule. We can only use it when events are independent. Here's an example. So Sam is late to work 20% of the time. Where he lives, it rains 25% of the time. On any given day, the probability that he is late and it is raining is 10%. Is his lateness independent of whether or not it rains? So the condition for that is the following. So this is just by the definition. So it's going to be independent if the probability of it raining and him being late is the same as the probability of it raining multiplied by the probability of him being late. So this left-hand side, probability that that it rains and he's late, well, we're told that it's 10%, so it's 0.1. What about the product of the probability? So the probability that it rains multiplied by the probability that he's late, well, that's the probability that it rains, which is 0.25, multiplied by the probability that he's late, which is 0.2, and that is 0.05. Now, these two things are not the same, right? 0.1 is not the same as 0.05. Okay, so the fact that these are not the same shows that these two events are not independent. Okay, so that's really it for independent events. We'll come back to it. It's just an important category because when it's true, we can use this AND rule, and when it's not true, we can't. See you in the next video when we're going to look at mutually exclusive events. Another important concept in probability is mutually exclusive events. So let's have a look at what that is. So consider these two events, rolling a 6, that's event A, and rolling a 5, that's event B. And consider this for the very same dice roll. Well, clearly you can't roll a 6 and a 5 at the same time on the same roll. And when that's the case, we've got mutually exclusive events. So these two events are what we call mutually exclusive because they cannot both happen. So written down formally, what we have is the following. If the probability of A and B happening, so if their intersection is 0, then we're dealing with mutually exclusive events. So that is the simple condition for mutually exclusive events. Now, the reason we're interested in mutually exclusive events is that they're easy to work with. Let me show you an example. Find the probability of rolling an even number on a dice. Well, what's that? So that's the probability of rolling a 2 or a 4 or a 6. Now, since these events are all mutually exclusive, they can't happen at the same time. This means we can just add their probabilities together. I can just work out the probability of rolling a 2, add it to the probability of rolling a 4, and add that to the probability of rolling a 6. And in this case, it's just a 6th plus a 6th plus a 6th, which is 3/6 or 1/2. So we can generalize this point that when we've got mutually exclusive events, we have the following rule, sometimes called the OR rule. If A and B are mutually exclusive events, then the probability of A or B, of one happening or the other happening, is just the probability of the first one plus the probability of the other one. Let's look at that on a Venn diagram. So mutually exclusive events are easy to spot because there's no overlap. So it would be something like this. Here is event A, and here is event B. So if we want the probability of A or B, it is simply all of that plus all of that. Okay, so what about when we don't have mutually exclusive events? So what would the OR rule be for non-mutually exclusive events? Well, let's look at the Venn diagram again, but this time we are going to have an overlap. So consider just a standard Venn diagram with two events. Here's A and here's B, and there is an overlap. So we want the probability of A or B, so we want this entire region. Well, let's start with the probability of A. So that's all of this. And I'm going to shade this carefully. You'll see why soon. So all of that is the probability of A. So I'm going to keep track of this. Now, if I then also add all of the probability of B, so all of this region, notice that I have, so I'll just add that in, Notice that I've counted the intersection twice. You can see that's been shaded 2 times. But of course, I only want to count it once. I don't want to double count any region. So I can compensate by simply removing that. So the probability of the intersection. So this is a formula for the probability of A or B that works in general. This is true for all events, mutually exclusive or non-mutually exclusive events. Just if they're mutually exclusive, this bit is 0. So you can use this regardless. It's just when they're mutually exclusive, it's simple because this little correction at the end is 0. Let's apply this in this case. So this is similar to a question we saw last video. So Sam is late to work 20% of the time. Where he lives, it rains 25% of the time. On any given day, the probability that he is late to work and it is raining is 10%. Find the probability that he's late to work or that it's raining. Okay, so let's use our formula here. So the probability that it's raining or he's late, we've now seen is the same as the probability that it's raining plus the probability that he's late minus the probability that it's raining and he's late. So we're looking for the probability that it's raining or it's late, and we've got all the information we need because the probability that it's raining is 0.25. The probability that he is late is 0.2. And the probability that it's raining and he's late is 0.1. So 0.25 plus 0.2 minus 0.1 is 0.35. So that is the probability that either it's raining or he is late on any given day. So we can use that rule in any situation as long as we have enough information. So that's mutually exclusive events, and also what the OR rule is, the addition rule is, for cases where events are not mutually exclusive. I'll see you in the next video. In this video, we're going to look at tree diagrams, a very powerful and useful technique for solving probability problems. So a tree diagram is a representational technique. It's a way for us to visualize a probability problem. It's useful in situations where there are a number of events, each with a kind of finite number of outcomes. Let's have a look at an example. So Tanya loves to play tennis, but especially so when the weather is good. When it is sunny, the probability that she plays tennis is 80%, and when it is not sunny, the probability is just 35%. There is a 60% chance that it will be sunny this Saturday. Find the probability that she plays tennis this Saturday. So what we can say is that whether she plays tennis or not depends to some extent on what the weather is. So we can start by considering the weather. What we can do is we can split two branches out. This one represents the outcome that it is sunny, and this one that it is not sunny. So S dash, that's a complement of S. And on the branch, I can write down the probability. So the chance that it's sunny this Saturday, the probability is 0.6, which means the probability that it's not sunny is 0.4. Now, if it's sunny this Saturday, we're told that there is an 80% chance she'll play tennis. It says when it is sunny, the probability that she plays tennis is 80%. So when it's sunny, she either plays tennis or she doesn't play tennis. Now, if it's sunny, there is an 80% chance she plays tennis and a 20% chance, therefore, that she doesn't play tennis. And if it's not sunny, well, she either plays tennis or she doesn't play tennis. And there is a 35% chance, 0.35 probability, she'll play tennis if it's not sunny, and therefore a 0.65 chance that she doesn't. So what's the probability that she plays tennis this Saturday? Well, it's either that it was sunny and she played tennis, or that it was not sunny, but she did play tennis. So the probability that it was sunny and she played tennis, well, that's 0.6 times 0.8. That's our AND rule in practice there. So that's 0.48. Okay, and then we've also got the chance that it's not sunny, but she does play tennis. So that's 0.4 times 0.35, and that is 0.14. And now we can just add these two together. That's the OR rule, right? These are mutually exclusive events because it's not possible for it to be sunny and she plays tennis and not sunny and she plays tennis. So we can just add those two. And when you add 0.48 and 0.14, you get 0.62. And so 0.62, that is the probability that she plays tennis this Saturday. So nice example of how we can use a tree diagram to solve a probability problem like that. Let's have a look at another. And this is a bit of a classic. Tree diagrams are great for when we're dealing with selections. So yeah, a bit of a classic is sort of sweets in a bag. So we've got 10 sweets in a bag, seven of them are red and 3 are blue. Chen picks 2 sweets at random from the bag, find the probability that they are the same colour. Well, let's use our tree again. Let's go with our first pick here. And that's either going to be red or blue. Now, what are our probabilities? Well, 7 of the 10 are red. So there is a 7 out of 10 probability of picking red. And then there's a 3 in 10 chance of picking blue, because clearly the other 3 are blue. We're told that as well. Now, that's our first pick. Now for our second pick. So if our first pick was red, then our second pick can still be red or blue. But if we picked red on our first pick, there are now not 7 red and 3 blue. There are now only 6 red and 3 blue. So the probability of selecting red on our second go is 6 out of 9. But there are still 3 blue in there. So that's 3 out of 9. Now, if we picked blue on our first go, our second pick can also be red or blue. If we picked 1 blue out of the bag first time round, then there are still 7 red left in the bag. But there are 7 out of 9 are red because there's 1 fewer sweet in the bag. And if I picked 1 blue the first time, there are now only 2 left. So 2 out of the remaining 9 are blue. So we want to know what's the probability they're the same colour. So that's either red followed by red or blue followed by blue. So red followed by red is 7 over 10 times 6 over 9. So that is 42 over 90. I'm going to worry about doing all my simplifying at the end, by the way. Or it's blue followed by blue. And that is, well, let's write down the calculation. It's 3 over 10 multiplied by 2 over 9. So that is 6 over 90. So then our overall probability is it was either red and red, which was 42 over 90, or, and there's the OR rule, it was blue and blue, and that was 6 over 90. Add these together and we get 48 over 90. And when we cancel and simplify, I think 6 goes into both of these and we get 8 over 15. So that's another example of how we can use tree diagrams to model a situation and use that to solve the problem. Hope that's been useful. I'll see you in the next video when we're going to look at Venn diagrams. Another great way to visualize and solve probability problems is using Venn diagrams. So that's what we're going to look at in this video. So we've already seen Venn diagrams in a couple of situations earlier on in this chapter. The point I want to start with in this video is that Venn diagrams can be used to represent numbers or probabilities. So I'm going to show you both. Let's start with numbers. So take a look at this. 100 people attend a conference, 40 of them drove a car to the conference, 30 of them are vegetarian, 20 of them are vegetarians who drove a car to the conference. Represent this information in a Venn diagram. So here we're representing numbers and not probabilities. So there are just 2 relevant categories in this question. So category number 1 is, did they drive a car to the conference? So that can be C. And the other category is, are they a vegetarian? I'm sure there are lots of other interesting things to learn about these people, but for now, that's all we're dealing with. So how can I start to fill this in? Well, 40 of them drove a car. Well, that means that the entirety of this C bubble adds up to 40. Well, that's 2 regions, so I can't really fill this in yet. Similarly, there are 30 vegetarians, so this entire bubble adds to 30. But I do know that 20 of them are vegetarians who drove a car to the conference, and that's the overlap here. So this must be 20. And now that I know that, well, I can figure the rest out, because if 40 of them drove a car, well, I've already got 20, so there must be 20 other people, so that this adds to 40, giving me 40 people who drove a car. And I've already got 20 vegetarians, and I need 30 in total, so I need 10 more in here. And finally, there were 100 people who attended the conference. I've got 10 plus 20 plus 20, that's 50. So I need a remaining 50 people, so that I now have 100 people. So with that information there, you could then ask questions, like what's the probability that, you make it up, what's the probability that someone drove a car but was not vegetarian, or various things like that. Once you've got the information there, you can see, let's actually answer that one. What's the probability that someone drove a car to the conference and was also not vegetarian? Well, how many people are there in that category? Well, it's these 20 people here. They're the car drivers who are not vegetarian. So 20 of those out of 100 people, and there's our probability, 0.2 or 20%. So that's how we can use Venn diagrams to represent numbers. Let's have a look at a more challenging example. This is, well, let's read it first. So a group of 100 people produced the following information relating to 3 attributes. The attributes were wearing glasses, being left-handed, and having dark hair. So let's first draw our Venn diagram. It's going to be a triple Venn diagram because of the 3 attributes. So everyone in this bubble are people who wear glasses. And then everyone in this bubble can be the people who are left-handed. And finally, everyone in this bubble, these can be the people who have dark hair. So that's D. And then I put this in a box. This is the entirety of my group. And now I can start filling the information in. And yeah, this can be fiddly, but pause and have a go at this yourself first, if you like. So here's the information. Glasses were worn by 36 people. So that's the entire glasses bubble. So I can't really fill that in yet. 28 people were left-handed. Well, that's multiple regions. I can't do that yet. And 36 had dark hair. Again, can't do that. There were 17 who wore glasses and were left-handed. So that's these 2 regions here, are the glasses and left-handed. 19 who wore glasses and had dark hair. So that's in the G and D category. And 15 who were left-handed and had dark hair. Only 10 people wore glasses, were left-handed, and had dark hair. So this is how we begin this. There are 10 people who have all 3 attributes. Okay, now that I've got that region in the middle, I can go back and start to piece the rest together. For example, I've got 15 people who were left-handed and had dark hair. So left-handed and dark hair is this region here. It's got to add to 15. I've already got 10, so 5 remains. Okay, there's 19 people who wore glasses and had dark hair. So this region has to add to 19. I've already got 10, so 9 remains. Then there's 17 people who wore glasses and were left-handed. So glasses and left-handed is here. And so this is a 7 to ensure that these 2 add to 17. And now I can fill in the rest because there were 36 people with dark hair. So all of this has to add to 36. So I've got 9 plus 10 is 19, plus 5 is 24. So that's a remaining 12 people with dark hair to ensure that the whole thing adds to 36. 28 people were left-handed. So what have I got already? I've got 7 plus 10 is 17, plus 5 is 22. So I need a remaining 6 to make sure that adds to 28. And for glasses, it should sum to 36. I've got 7 plus 10 is 17, plus 9 is 26. So that leaves 10 people left. Okay, now I can figure out what goes on the outside. I just need to see what I've got so far here, because I know that I need 100 people in total. So what have I got so far? 10 plus 7 is 17, plus 6 is 23, plus 5 is 28, plus 10 is 38, plus 9 is 47, plus 12 is 59. So that leaves 41 left on the outside who don't fall into any category. And then again, from this point, we could ask or solve probability problems, but the challenge here was just how do we represent it. So that's how you use Venn diagrams to represent numbers. But we also can use it to solve probability problems. Consider this. Alice and Bilal are sometimes late for work. Probability that Alice is late, but Bilal is not, is 0.32. The probability that Bilal is late, but Alice is not, is 0.11. And the probability that at least one of them is late is 0.65. And the overall question is determine whether or not the student's lateness is independent of each other. So we know how to test that, but let's try to represent this on a Venn diagram. So the two events are going to be that Alice is late, let's call that A, and that Bilal is late, let's call that B. So here's A, here's B. And what are we told? We're told the probability that Alice is late but Bilal is not is 0.32. So that's this region here. Alice A but not B. And then we've been told the probability that Bilal is late but Alice is not is 0.11. So that's this one here. And the probability that at least one of them, so that's anything in this whole region, is 0.65. Well, I've already got 0.32 and 0.11. So that is 0.43. And if I subtract that from 0.65, I get 0.22. So that's what's going in the middle here. Now, for good measure, I'll just work out what goes on the outside. So I've got 0.32 plus 0.22, that's 0.54. Plus this is 0.65. So the outside is 0.35. So now I can determine whether these events are independent. And I can do that using my test. My test, remember, is if P, A, and B is the same as PA times PB. So what's probability of A and B? Probability of A and B is 0.22. Okay, that we already calculated in the middle here. Probability of A times probability of B, well, that's the total probability of A, so 0.32 plus 0.22, so that's 0.54. And the probability of B, that's these two added, so 0.22 times 0.11 plus 0.11, that's 0.33. And if I multiply these two together, I get 0.178. And so these two things are not the same, and therefore the events are not independent. So again, it's a useful representation. Okay, I can quickly see what the probabilities are. I can keep track of the information and use that to solve certain questions, like determining whether events are independent or not. Okay, one more example here. So this is a bit more of an abstract one. So we've got probability of A is 0.35, probability of B is 0.45, and probability of C is 0.2. I'm also told that probability of A and B is 0.13. So given that A and C are mutually exclusive and that B and C are independent, draw a Venn diagram representing this information. Okay, there's quite a lot going on here, but the first thing I'll notice is that A and C are mutually exclusive. So there's going to be no overlap. So if that's A, then we better put C over here. So there's no overlap at all. So here's A and here is C. But B, there is going to be overlap with both. We weren't told that it was mutually exclusive with either. And so this is the setup. And now I'm going to fill in as much of the information from the question as I can. So what have we been given? We've been told that probability of A and B is 0.13, so that's this here. I've also been told the probability of A is 0.35, so this whole thing has to add to 0.35. So what's left over when I subtract 0.13 from 0.35? Well, that's 0.22. What else do I know? Well, I know that probability of B is 0.45, but I can't fill that in yet because there are two regions. And probability of C is 0.2. But I do know that B and C are independent. So if B and C are independent, I can use the AND rule. That's the probability of B and C is just the probability of B, which is 0.45, multiplied by the probability of C. We'll multiply those two together and I get 0.09. So that's what goes in here, 0.09. And now I can fill in the rest because B has to add to 0.45. I've already got 0.13 and 0.09. These two add to 0.22. So what's left to get me to 0.45? It's 0.23. What about C? C has to add to 0.2. I've already got 0.09, so 0.11 remains. Finally, I just need to figure out what goes on the outside. So I see what I've got already, so I add these up. So this plus this is 0.35, plus this is 0.58, plus this is 0.67, and plus this is 0.78. So what's left? Well, I can just do 1 minus 0.78, and I get 0.22. And so that's what's on the outside. And so there's the full information represented on a Venn diagram. Again, ready for us if we wanted to answer questions. Okay, that's all for Venn diagrams now. We're going to use them more when we look at things like conditional probability. I hope that's been a useful and enjoyable look at how we use them. See you in the next video. So now we're getting on to what I think is probably the most interesting part of this, and that's conditional probability. Let's have a look at how we work these kind of questions out. So conditional probability is when you're working out the probability of an event given some additional piece of information. So the probability of something conditional on something else that you know. So this is where the Bayesian way of thinking really comes in, because the probability that we believe for an event happening changes once we're given additional information. So let's go back to our characters here. So find the probability of a randomly selected character wearing glasses given that they are a dog. So what does that mean? Well, it means the following. It means, so take a look at this question. Find the probability of a randomly selected character wearing glasses given that they are a dog. So here's how we write this. It's that vertical dash, and this is pronounced probability of G given D. So what does that look like? Well, given that they are a dog means we are only looking at the three dogs. And what's the chance of one of these three dogs wearing glasses? Well, it's 1 out of 3. One of these dogs wears glasses, and hence the probability is 1 out of 3. So that's at the heart of conditional probability. It's that denominators change to reflect your information. We no longer have to look at anything other than the dogs because we are told that they are a dog. Now let's generalize this, and I'm using H and E, and you can think of those as standing for the probability of a hypothesis given certain evidence. Well, what you saw in the previous example is when you're looking for the probability of a certain event given some other event, you restrict your focus to the thing that you were given. So in the previous example, we were told that the character was a dog, so we only looked at the dogs. So here we've been given E. So given E means I'm now only going to be looking in this bubble here. So my probability is going to be out of whatever I see in that bubble. So it's going to be out of whatever is in here, whether that's a number or a probability. And so that's the probability of E here. And what's the probability of H given E? Well, it's the probability of being in H, which is this part here, given that you're also in E. Right? It can't be this bit of H over here because that's not in E. The only bit of H that is in E is this bit. So it's what's the probability that we're in this overlap region out of the probability that we're in this entire region. So what's the overlap region here? Well, that's the probability of H and E, the intersection. So this is the conditional probability formula that we're going to be using in this video. It's related, this is a sort of simplified version of Bayes' theorem, which we'll look at in the next video, but it's going to be good enough for everything that we need to do in this video. So let's see how we can use this in an actual example. So here is a completed Venn diagram. How we work out the probability of P given, the probability of H given E. So that's the probability of some particular hypothesis given the evidence. So what is the probability of H given E? Well, it's the probability of the intersection divided by the probability of E. So that's all of this added together. So 0.15 plus 0.2 is 0.35. And if we want, we can simplify that. That comes out to 3/7. So the probability of H given E in this case was 3/7. So that's a simple application of our conditional probability formula. Let's now apply it to a slightly more challenging case. So Amira and Jane are sometimes late to work. 70% of the time, neither of them is late. Amira is late 20% of the time, while Jane is late 25% of the time. Last Monday, Jane was late. Find the probability that Amira was late. Okay, a lot of information here. Let's try to put this information into a Venn diagram. So let's let this be the event that Amira is late, and let's let this be the event that Jane is late. And let's try to fill in as much as we can. So what can we fill in immediately? Well, 70% of the time, neither of them is late. Okay, so I know that this adds to 0.7. The outside region is 0.7. Okay, now there's the tricky bit. So Amira is late 20% of the time. So this should add up to 0.2. And Jane is late 25% of the time. So this should add to 0.25. The question is, what's the overlap? Well, here's how we can work it out. I know that all of this region, that's the region representing Amira being late, should add to 0.2. So if I know that that's 0.2 and that's 0.7, the only region I've not accounted for is this J but not A region. Well, 0.2 plus 0.7 is 0.9. That leaves 0.1 left to get us up to 1. And once I know that, I can work out this, because the probability of Jane being late is 0.25. I've already got 0.1, so 0.15 remains. And finally, Amira is late 20% of the time. I've already got 15%, so I need 5%. And so now I've got the completed Venn diagram, I can now tackle this question. So last Monday, Jane was late. So that's the information I've been given. Find the probability that Amira was late. So I'm being asked to find the probability that Amira was late, given that Jane was late. The information I was given, the evidence I've been given, is that Jane was late. So we can use our conditional probability formula. It's the probability of the intersection of A and J, the probability they're both late, divided by the probability that Jane was late. So what do we get? Well, the intersection is 0.15, and the probability that Jane was late is 0.25. So 0.15 divided by 0.25, and that is simplifies down to 3/5. And so there's our answer. You could give that a percentage, 60% if you like. But there's how we can use conditional probability to solve a problem like that, using a Venn diagram in that case. Okay, let's now see how we can use a tree diagram to solve a conditional probability problem. So this is similar to a question we looked at in the tree diagram video. Titania loves to play tennis, but especially so when the weather is good. When it is sunny, the probability that she plays tennis is 80%, and when it's not sunny, the probability is just 35%. There is a 60% chance that it is sunny on any given day. last Saturday she played tennis. What's the probability that it was sunny last Saturday? Okay, so overall the question is, what's the probability that it was sunny last Saturday, given that she played tennis? We've been told that she played tennis. So H, our hypothesis, is going to be that it was sunny last Saturday. That's the thing we're investigating. And our evidence is that Tanya played tennis. So let's construct our tree diagram. So whether she plays tennis depends to some extent on the weather. So I should start my tree with whether it was sunny or not. So that's H or not H. It was sunny or not. Now, it's sunny 60% of the time, and therefore it's not sunny 40% of the time. Okay, now if it was sunny, then our evidence, so that's whether she played tennis, that's going to be true 80% of the time, because we're told that when it's sunny, she plays tennis 80% of the time, and when it's not sunny, when it's sunny, she doesn't play tennis, therefore 20% of the time. When it is not sunny, so H dash, there is a 35% chance of playing tennis, and therefore there's a 65% chance of not playing tennis. Okay, with me out of the way, there's room to work. So let's first consider our formula. So our formula here, so the probability that the hypothesis that it was sunny is true, given the evidence, is the probability of the intersection, so probability of H and E, divided by the probability of E. So we just need to work out all of these probabilities. So the one at the top is not too bad, because the probability of H and E is just the probability of H multiplied by the probability of E given H. So that's 0.6 times 0.8. So 0.6 times 0.8, and that's 0.48. Okay, what about the probability of E? Well, that could be H and E, or it could be not H and then E. So there's two ways of getting that. So the probability of E, that's 0.6 times 0.8, which we already know, plus this branch here, 0.4 times 0.35. 0.4 times 0.35. So in total, what is that? That's 0.48 plus 0.14, which is 0.62. So our answer is just 0.48, so the probability of H given E is the intersection, which is 0.48, divided by probability of E. And that's about 0.77. So there's our answer. With the evidence that she played tennis last Saturday, we can now conclude that there was a 77% chance that it was sunny last Saturday. So there's a nice example of conditional probability using a tree diagram. So that's all on conditional probability for now, but in the next video I'm going to look at Bayes' theorem, which is really just a development on this, showing the full picture in all its glory. So I'll see you there. To conclude this chapter, we're going to look at Bayes' theorem. This video is a bit of an extension, so it's a bit more technical than the others, but I hope you enjoy it. Bayes' theorem is a big deal in statistics. It represented a huge step forward in how people understood probability. In the last video, I showed you this. Now, this is a simple conditional probability formula. It's perfectly valid, it's not wrong, but it's not quite the full picture. So in this video, I'm going to develop the full Bayes' theorem, show you how it's true, why it works, and how we can use it. So I'm going to start with a very famous little supposed paradox. Suppose there is a disease, call it disease X, and it affects 10% of people where you live. Now, you go to a doctor and you are tested for this disease, and the test says you have disease X. Thing is, the test gives the correct result 80% of the time. Regardless of whether you have the disease or not, it will correctly diagnose you 80% of the time. So the question is, what is the probability that you have the disease? Well, you might want to pause and just think what you think the right answer to that question is. Okay, let's visualize this problem. So we're going to do this by imagining 100 representative people. So let's say this person has the disease, this person, and so on. We know that 10% of the people have the disease, and let's say here are those 10. So let's just organize it so that the 10 people with the disease are all down here. And let's also say that because 20% of the time the test gives the wrong diagnosis and 80% it gives the right, that on this dotted line, this represents to the left of the people who the test correctly diagnosed, and to the right, the people who are incorrectly diagnosed. So these people here are the ones who don't have the disease, who are correctly told they don't. These people don't have it, but were incorrectly told that they do. These people here had it, but incorrectly told that they don't. And the bottom right were the ones who had it and were correctly told they do. So here are the healthy people. Here are the people who have the disease. Here are the people who got the correct test result. And here are the people who got the incorrect test result. So everyone is going to be in one of those 4 categories. So remember that the test says that you have the disease. So which one of these people could you be? Well, let's see. Well, you can't be those people because they were told correctly they don't have it. You also can't be these people because they were incorrectly told that they don't have it. You were told that you do. So you must be either one of the yellow people or one of the red people. One of them or one of them. So we can ignore everyone else. So we can rephrase the question as, given that you are either one of the yellow people or one of the red people, what's the probability to have the disease? Remember that the yellow people, well, they were people who had the disease, who were told that they do, and the red people were people who did not have it, but were incorrectly told they do. So out of these people, what's the probability that you are one of the yellow ones? Because they're the ones with the disease. Well, there's 8 of them, and there's 18 people who don't have it, who are incorrectly told that they do. So this is the probability calculation. It's the probability of being yellow, there's 8 of those, out of 26. That's the number of people there. And what's that? Well, it is about 31%. So here's the situation. The test says you have disease X. Disease X affects 10% of the people where you live. The test gives the correct result 80% of the time. We've now just seen that there is a 31% chance you have the disease. Quite a surprising result. Most people's intuition is that it's 80 because the test is correct 80% of the time. It said you had the disease. So let's start again and say there are a certain number of people. Let's try to just be completely general here. So the number of people who have the disease is just the total number of people multiplied by the probability of having the disease. Now, if we want the number of people who have the disease and were correctly told that they do, that's the yellow people, it's the number of people multiplied by the probability of having the disease multiplied by the probability of getting a correct diagnosis, a positive result, given that you have the disease. In this case, that was 80%. We multiplied by 80%, and that's the t given x. Right? That's the probability that the test says you have the disease, given that you have the disease. And so that's the probability of our, or really that's like the number of yellow people in our case here. It's the total number of people times the probability of having the disease times the probability that the test says you have it, given that you have it. And in our case, that was the number of people, 100 times 0.1, that was the chance of having the disease overall, times 0.8, that's the chance of correctly being told that you do. What about the red people? Well, we can calculate that number in the following way. We start with the number of people. We multiply by the probability of not having the disease. In our case, that was 0.9. And then we multiply by 0.2. That's the chance of being told you have the disease, a positive test result, given that you don't. And so those blue people, who I'm now going to colour red, well, that's just the total number of people times the probability of not having the disease, 0.9, times by the probability of getting a positive test result, given that you don't have it, which was 0.2. So let's piece these together into our formula. We said that it was the probability or the total number of people who had the disease, that's just the yellow people here, divided by the total number of people who got told they do. It's the total number of people who... So let's piece this together. So given that we've received a positive test result, so given that we're either one of the yellow people or the red people, the chance that we have the disease is the number of people who had it out of these, which was just the yellow people, divided by the total number of people who got a positive test, which was the yellow people plus the red people. So let's just tidy this up. Notice that we can just cancel the total number of people. That's the overall probability is independent of that. And let's just neaten this up now. So here's the formula that we've reached. Now, all I'm going to do is replace X with H. Remember, H stands for hypothesis. In our case, it's the hypothesis that we have the disease. And I'm going to replace T, that's the receiving a positive test result, with E. Okay, and that's E for evidence. The evidence is you get a positive test result. Just rearrange these a little bit, and this is Bayes' theorem. So let's have a look at this in relation to our diagram before. So that numerator, well, that's just the yellow dots down there. So that's the people who had the disease and were correctly told that they do. So P of H, that's that they did have the disease, and then multiplied by the probability of the evidence that they were told that they do, given that they in fact have the disease. And then that appears again on the denominator, but so do these red people here. That's the people who did not have the disease, but were told incorrectly they do. That's probability of H dash, so that's the probability of not having the disease, multiplied by the probability that the evidence was still seen, given that they don't have it. So that's they still received a positive test, even though they don't have it. So there it is. That is Bayes' theorem. Now, this was made, or at least a very famous example was made in Daniel Kahneman's book, Thinking Fast and Slow. Let's take a look at this. So Steve is very shy and withdrawn, invariably helpful, but with very little interest in people or in the world of reality. A meek and tidy soul, he has a need for order and structure and a passion for detail. With that in mind, the question posed was, do you think he's a farmer or a librarian? Now, with that description, most people would be tempted to think that it is much, much more likely that he is a librarian. But what we failed to take into account, and what Bayes' theorem can help us with, is the absolute number of farmers versus the absolute number of librarians. Let's take a look at this. Now, in many Western countries, there are far, far more farmers than librarians. So let's say there are 10 times as many farmers as librarians. So I've represented this with 100 green farmers and just 10 yellow librarians. So let's see if we can work through this now. So suppose that it's the case that 30% of farmers conform to this description. And by the way, the whole point is this description is one that we would normally associate with librarians. And let's also say that 90% of librarians conform to this description. So I've got a large number of farmers, most of whom don't conform to this description, but a reasonable percentage do. Those are the green dots. And I've got a small number of librarians, almost all of whom conform to this description, and those are the yellow dots. So now the question is, given that this description holds, so given that we are one of these people, what's the probability that we are a librarian or a farmer? So farmers to librarians, what's the ratio? Well, if we just count the dots, it's 30 to 9. So put another way, there's a 77% chance that someone conforming to that description is a farmer and a 23% chance they're a librarian. So our intuitions were wrong. We see that description and we think, oh, that's definitely a librarian. But that's because we failed to account for the fact that there are far more farmers than there are librarians. And when we factor that in, what we find is it is in fact more likely to you randomly select a farmer who has all of those characteristics than a librarian who has those characteristics. That's, I think, a really nice example of Bayes' theorem in action. So let's now plug all of this into our formula. So the probability that Steve is a librarian, given that he's shy, tidy, etc. So we first start with the probability that he is a librarian in general. So that is just, well, it's 10 out of 110, so it's 1/11th. And then we say what fraction of those librarians meet that description. So that's the probability of him being shy, etc., given that he's a librarian. And we said that was 90%. And now we're going to divide that by, well, it's the same thing again. That's those 9 people. Plus, okay, we're going to build this up. So the probability that he's not a librarian, so that's all of those green people, it's out of the whole number, so that's 100 out of 110. And then multiplied by the probability of being shy, given that you're not a librarian. So that was 30% in our example. So on our numerator, we've got 10 out of 110 multiplied by 9 out of 10. And on the denominator, it's the same calculation again. And then for farmers, it's 100 out of 110 multiplied by 30 out of 100. Crunch through the numbers there, and we get 23%. So there it is in action. Final bit of jargon about Bayes' theorem. Well, the probability of the hypothesis before you consider the evidence, that's called your prior. So that just might be, if you just randomly selected someone, what's the probability that they're a librarian? That's your prior, before you've seen the evidence. Your posterior, well, that's your updated view. Now that we've seen the evidence, this is your new opinion. Likelihood, well, that's the probability that that evidence is true given the hypothesis. So that would be the probability of seeing this sort of shy, conscientious person given that they're a librarian. And all the stuff on the bottom is sometimes called the evidence and sometimes called the marginal likelihood. And that denominator, by the way, is just the same as the probability of E, because it just accounts for all of the ways in which E could happen. So that's a kind of simplified form, but you often don't have the probability of E overall. You often have to split it up, as we've seen in the previous examples. So I hope you enjoyed looking at Bayes' theorem. It is a bit of a beast of a formula, but I think knowing where it comes from is just a really enjoyable mathematical experience. So I hope you enjoyed working through that. That concludes our work on probability and also concludes this course for now. Thank you very much for joining me through this, and I look forward to seeing you soon.